If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The enigma of singularities, a gateway to the unknown. Imagine standing at the edge of a cosmic abyss, a place where time seems to halt, space twists into incomprehensible shapes, and the very laws of physics dissolve into chaos. Singularities, the enigmatic centers of black holes and possibly the origin point of the universe itself, are not just scientific abstractions. They represent the ultimate frontier of human understanding, where the known gives way to infinite possibilities and profound mysteries. But what exactly are these elusive phenomena, and why do they captivate the minds of scientists and dreamers alike? To grasp the significance of singularities, one must first understand the framework that predicts their existence: Einstein's general theory of relativity. This revolutionary model transformed our perception of the universe, showing that gravity is not merely a force but the curvature of space-time caused by mass and energy. Singularities are the points where this curvature becomes infinite, places where our mathematical tools and physical intuitions collapse under the weight of infinity. These are not mere oddities and equations, but the very fabric of reality stretched to its breaking point. A singularity, in its simplest description, is a region where density becomes infinite and space-time curvature is unfathomably steep. To visualize this, think of a rubber sheet representing space-time. Placing a ball on this sheet creates a dent, much like a planet or star bends space-time. But a singularity is akin to punching a hole straight through the sheet, a point where the sheet itself ceases to exist. It's a realm where our current understanding falters, leaving physicists grappling with the unknown. Black holes, perhaps the most famous manifestations of singularities, serve as cosmic laboratories for these extremes. Formed from the remnants of massive stars that have exhausted their nuclear fuel, black holes condense matter into a point of near-infinite density. The gravitational pull becomes so intense that nothing, not even light, can escape. But the story doesn't end there. At the heart of every black hole lies the singularity, shrouded by the event horizon, the boundary beyond which no information can escape. The nature of singularities challenges some of the most foundational concepts in physics. How can the universe allow such a breakdown in its own rules? General relativity provides a macroscopic view of singularities, describing their immense gravitational pull and warping effects. However, the quantum realm, which governs the behavior of the tiniest particles, paints a very different picture. One where probabilities, uncertainties, and strange phenomena dominate. Reconciling these two views is one of the greatest scientific challenges of our time, pushing researchers toward the elusive goal of a unified theory of quantum gravity. Singularities are not confined to black holes. They also play a pivotal role in our understanding of the cosmos. The Big Bang Theory suggests that our universe began as a singularity, a point of infinite density and temperature from which all matter and energy expanded. This raises profound questions. Was the Big Bang a true singularity, or is it simply the limit of our mathematical descriptions? What, if anything, existed before this cataclysmic event? These mysteries lie at the heart of cosmology, prompting us to rethink our place in the grand tapestry of existence. The more we study singularities, the more they seem to defy categorization. Theoretical models propose various types, including naked singularities, which lack the event horizon shielding them from the universe, and white holes, the hypothetical opposites of black holes that expel matter and energy rather than consume them. While these ideas remain speculative, they challenge our understanding of the cosmos and open the door to bold new theories. Yet singularities are not just abstract puzzles. They carry profound implications for reality itself. Could they be portals to other dimensions or universes? Are they the key to understanding the flow of time and the nature of space? These questions push the boundaries of human imagination, blending science with philosophy in a quest for answers. As we peer deeper into the cosmos with powerful telescopes and advanced simulations, singularities remain tantalizingly out of reach, both literally and figuratively. But their allure lies precisely in their mystery. They are the ultimate why of the universe, inviting us to journey beyond the stars and into the heart of the unknown. The anatomy of a singularity. Peering into the heart of a singularity is akin to attempting to glimpse the soul of the universe itself, a venture fraught with paradoxes, mysteries, and tantalizing glimpses of hidden truths. Singularities represent the ultimate limits of space-time, where the very fabric of the cosmos tears apart under the crushing weight of gravity. But what lies at their core? What makes them so unique? And how does our understanding of their anatomy shape the broader tapestry of physics and cosmology? At the center of a black hole lies the singularity, a point where density reaches infinity and the laws of physics as we know them cease to function. The journey toward understanding this enigmatic region begins with the concept of space-time curvature. In Einstein's general theory of relativity, massive objects distort the space-time around them, creating what we perceive as gravity. Singularities take this distortion to an extreme. Instead of bending space-time, they fold it so dramatically that it effectively becomes a tear, a discontinuity where the curvature becomes infinite. The mathematics of singularities offers a fascinating yet perplexing insight into their nature. The Schwarzschild solution to Einstein's equations, for instance, describes a non-rotating black hole. This solution predicts a singularity as a one-dimensional point of infinite density and zero volume, surrounded by an event horizon. But if the black hole rotates, as most are believed to do, the singularity takes on a different form, an infinitely thin ring. This ring-shaped singularity, described by the Kerr solution, introduces intriguing possibilities, including theoretical pathways to other regions of space-time or even alternate universes. A key feature of singularities is their effect on space-time itself. As matter approaches a singularity, it undergoes immense tidal forces, a phenomenon known as spaghettification. These forces stretch objects lengthwise while compressing them widthwise, ultimately reducing them to their constituent particles. This dramatic deformation is not merely theoretical. It is a natural consequence of the extreme gravitational gradients near a singularity. For any object unlucky enough to approach, the journey ends in complete disintegration. Despite their reputation as regions of destruction, singularities are also places of creation, at least in the context of theoretical physics. They serve as cosmic engines, driving the dynamics of black holes and influencing the behavior of the surrounding universe. Their immense gravitational pull can trap stars, gas, and even other black holes, forming vast accretion disks and generating high-energy jets that extend across millions of light years. These jets, powered by the singularity's extreme environment, are among the most energetic phenomena in the universe, capable of shaping entire galaxies. The anatomy of a singularity is not limited to its physical characteristics. It also encompasses its influence on the flow of time and the perception of reality. Near a singularity, time slows dramatically due to the intense gravitational field, a phenomenon predicted by relativity and confirmed by experiments. This time dilation means that an external observer watching an object fall toward a black hole would see it slow down and appear to freeze at the event horizon. For the object itself, however, time continues to flow normally, leading it inexorably toward the singularity. Understanding the inner workings of singularities requires bridging the gap between general relativity and quantum mechanics, a challenge that has eluded physicists for decades. General relativity describes singularities as deterministic entities governed by precise mathematical rules. In contrast, quantum mechanics introduces uncertainty and probabilistic behavior, suggesting that singularities may not be as well defined as they appear. This clash between two foundational pillars of physics underscores the need for a theory of quantum gravity, which could unlock the secrets of singularities and reconcile these seemingly incompatible perspectives. One of the most profound questions surrounding singularities is their ultimate nature. Are they true points of infinite density, or do they represent a breakdown in our current understanding of physics? Some theories suggest that singularities are not infinitely small, but instead have a finite, albeit incredibly dense structure. Others propose that singularities are hidden behind a veil of quantum effects that prevent us from observing their true nature. These ideas challenge the traditional view of singularities as absolute endpoints and hint at a deeper layer of reality yet to be discovered. The study of singularities is not confined to theoretical models. Observational evidence plays a crucial role in shaping our understanding of these cosmic phenomena. Instruments like the Event Horizon Telescope have provided unprecedented images of black holes, offering a glimpse into the regions surrounding singularities. These observations, combined with gravitational wave detections from colliding black holes, bring us closer to unraveling the mysteries of singularities while raising new questions about their behavior and interactions. The anatomy of a singularity is as much about what we do not know as it is about what we do. It represents a convergence point for some of the most profound concepts in physics, from the nature of space and time to the limits of human knowledge. Each discovery about singularities peels back another layer of the cosmic onion, revealing a deeper, more intricate reality that challenges our assumptions and expands our horizons. Cosmic cauldrons, black holes, and beyond. When contemplating the mysterious singularities that inhabit our universe, one cannot avoid their most dramatic manifestations: black holes. These cosmic entities, born from the collapse of massive stars or through the accumulation of matter over time, are the ultimate laboratories for studying the extremes of physics. But what lies beyond their enigmatic event horizons? Could they hold the answers to the deepest questions about our universe? Or do they merely hide the unknowable? A black hole is more than just a singularity at its core. It is a dynamic and multifaceted phenomenon that shapes the cosmos on scales both immense and intimate. At the heart of a black hole lies the singularity, an object of unimaginable density where the gravitational pull becomes infinitely strong. Surrounding this singularity is the event horizon, the boundary beyond which no information can escape. This is the defining feature of a black hole, a region from which not even light can emerge, rendering it invisible against the backdrop of space. The formation of black holes begins with the death of massive stars. When such a star exhausts its nuclear fuel, it can no longer counteract the inward pull of gravity with the outward pressure generated by fusion. The star collapses under its own weight, and if its mass exceeds a critical threshold, no known force can halt this collapse. The result is the creation of a singularity, enveloped by an event horizon. A black hole is born. This process is not merely theoretical. Astronomers have observed the remnants of supernovae, the explosive deaths of stars, which often leave behind neutron stars or black holes. Black holes come in various sizes, ranging from stellar mass black holes a few times the mass of our Sun to supermassive black holes millions or even billions of times more massive. These supermassive black holes are typically found at the centers of galaxies, including our own Milky Way, where the supermassive black hole Sagittarius A* resides. How these colossal objects form remains an open question, with theories suggesting either the collapse of massive gas clouds in the early universe or the gradual growth of smaller black holes over billions of years. The event horizon is not the only feature of a black hole that captures the imagination. Surrounding many black holes is an accretion disk, a swirling maelstrom of gas and dust spiraling inward. The intense gravitational pull heats this material to millions of degrees, causing it to emit brilliant X-rays and other radiation. These emissions are often the first clues that astronomers use to identify the presence of a black hole, as the black hole itself remains invisible. Beyond the accretion disk, black holes can produce powerful jets of high-energy particles that extend across vast distances. These jets, driven by magnetic fields and the rapid rotation of the black hole, can stretch for thousands of light years, influencing the formation of stars and the structure of galaxies. Observing these jets provides crucial insights into the mechanics of black holes and their impact on the universe. As we explore black holes further, intriguing questions arise about what happens to the matter and energy they consume. According to classical physics, anything that crosses the event horizon is irrevocably lost to the singularity. However, quantum mechanics suggests a more nuanced picture. Stephen Hawking famously proposed that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation allows black holes to slowly lose mass and energy, potentially evaporating entirely over immense timescales. Hawking's work also raises the profound information paradox. If a black hole eventually evaporates, What happens to the information contained in the matter it swallowed? Does it vanish forever, violating the laws of quantum mechanics? Or is it somehow preserved? Resolving this paradox is one of the most pressing challenges in modern physics, with implications for our understanding of both black holes and the fundamental nature of information. Black holes also challenge our understanding of time and space. Near the event horizon, time slows down due to the immense gravitational field, a phenomenon known as gravitational time dilation. For an observer far from the black hole, time appears to move normally, but for someone falling toward the event horizon, time slows to a crawl. This warping of time and space is not merely a theoretical curiosity. It has been confirmed through observations and experiments, such as the bending of light around massive objects. The study of black holes is not limited to the present. It also has profound implications for the future of the universe. As stars die and galaxies evolve, black holes are expected to play an increasingly dominant role in shaping the cosmos. In the distant future, as stars exhaust their fuel and galaxies disperse, black holes may remain as some of the last remnants of structure in the universe. Their eventual evaporation through Hawking radiation could mark one of the final stages in the cosmic timeline. Black holes are not the only objects associated with singularities. Theoretical physics suggests the existence of other exotic phenomena, such as white holes and wormholes. White holes, the hypothetical opposites of black holes, are regions that expel matter and energy rather than consume them. While no evidence for white holes has been observed, they remain an intriguing possibility in the equations of general relativity. Wormholes, or Einstein-Rosen bridges, offer another fascinating extension of black hole physics. These hypothetical structures could connect distant points in space-time, potentially serving as shortcuts for interstellar travel or even links to other universes. While wormholes remain speculative, their study provides valuable insights into the nature of space-time and the interplay between gravity and quantum mechanics. As we continue to unravel the mysteries of black holes and their singularities, we find ourselves on the edge of a profound revelation. These cosmic cauldrons challenge our understanding of the universe, forcing us to confront the limits of knowledge and the boundaries of reality. What lies beyond the event horizon? What secrets are hidden within the singularity? The answers to these questions promise to reshape our view of the cosmos and our place within it. The Big Bang. Was it a singularity? Rewind the cosmic clock to the earliest moments of existence, and you'll find yourself face to face with a profound mystery, the Big Bang. This monumental event, the genesis of our universe, holds within it the tantalizing possibility of a singularity, a point where density and temperature were infinite and the known laws of physics ceased to function. But was the Big Bang truly a singularity, or does its nature defy such a simplistic interpretation? To understand the connection between the Big Bang and singularities, we must first delve into the foundations of modern cosmology. The Big Bang theory posits that the universe began approximately 13.8 billion years ago, expanding from an incomprehensibly hot and dense state. This expansion, driven by forces still not fully understood, set the stage for the formation of galaxies, stars, and planets, and ultimately, the emergence of life. The evidence for this theory is overwhelming. The cosmic microwave background radiation, the large-scale structure of the universe, and the observed redshift of distant galaxies all point to a universe that was once much smaller and denser. But what came before this expansion? As we trace the universe's history backward in time, we encounter a moment where temperatures and densities rise to unimaginable levels. This is where the concept of a singularity enters the picture. According to classical general relativity, the equations governing the universe's evolution break down at this point, leading to a state of infinite density, a singularity. However, this interpretation raises more questions than it answers. One of the central challenges in describing the Big Bang as a singularity is the clash between general relativity and quantum mechanics. While general relativity provides a robust framework for understanding the large-scale structure of the universe, it fails to account for the quantum effects that dominate at extremely small scales. The early universe, where densities and temperatures were extraordinarily high, falls squarely into the quantum realm. This suggests that a complete understanding of the Big Bang requires a theory of quantum gravity, a unification of the principles of relativity and quantum mechanics. Several competing theories attempt to resolve this puzzle. One prominent idea is the concept of cosmic inflation, a rapid exponential expansion that occurred fractions of a second after the Big Bang. Inflation smooths out irregularities and explains the observed uniformity of the cosmic microwave background. However, it also raises the possibility that the Big Bang was not a singularity in the strict sense. Instead, it might represent a transition from a prior state, a pre-Big Bang era that remains hidden from direct observation. Another intriguing possibility is the idea of a bouncing universe. In this scenario, the Big Bang was not the beginning, but a moment of transition from a previous contraction phase. This cyclic model suggests that the universe undergoes endless cycles of expansion and contraction, with each Big Bang representing a new beginning. Such theories challenge the traditional view of the Big Bang as a singularity and open the door to a deeper understanding of the cosmos's origins. The quantum perspective offers even more radical insights. Loop quantum cosmology, a branch of theoretical physics, proposes that space-time is not continuous but composed of discrete, quantized units. According to this framework, the universe's density and curvature are finite, even at the earliest moments. This eliminates the singularity and replaces it with a quantum bounce, where the universe transitions smoothly from one phase to another. While still in its infancy, loop quantum cosmology represents a promising avenue for reconciling the Big Bang with quantum principles. The question of what came before the Big Bang remains one of the most tantalizing mysteries in cosmology. Traditional interpretations suggest that time itself began with the Big Bang, rendering the concept of before meaningless. However, alternative models, such as the multiverse hypothesis, propose that our universe is just one of many, each with its own timeline and set of physical laws. In this view, the Big Bang might represent the birth of our particular universe within a broader multiverse framework. The Big Bang also raises profound philosophical and existential questions. If the universe emerged from a singularity, does that imply a deeper underlying order or purpose? Or is the universe a spontaneous, uncaused phenomenon governed by chance? These questions extend beyond the realm of physics, touching on metaphysics and the nature of existence itself. Observational efforts continue to shed light on the earliest moments of the universe. Instruments like the James Webb Space Telescope and the study of primordial gravitational waves aim to probe the conditions of the infant cosmos, seeking clues about the nature of the Big Bang. These observations hold the potential to confirm or challenge existing theories, guiding us closer to the truth about our origins. As we contemplate the Big Bang, we are reminded of the profound interconnectedness of time, space, and matter. Whether it was a singularity, a quantum bounce, or something entirely different, the event that gave birth to the universe is a testament to the beauty and complexity of existence. It is a reminder that even the most fundamental questions can lead to infinite possibilities, inviting us to explore the cosmos with curiosity and wonder. White holes, myth or reality? Imagine a cosmic phenomenon that expels matter and energy rather than consuming it, a celestial counterpart to black holes that operates in reverse. This is the concept of a white hole, a theoretical construct that emerges naturally from the same equations of general relativity that predict black holes. But are white holes merely mathematical curiosities, or could they represent real phenomena hidden within the vastness of the universe? To understand white holes, we must first revisit the properties of black holes. At their core, black holes are defined by their event horizons, boundaries beyond which nothing can escape. White holes, by contrast, are proposed to have event horizons that cannot be crossed from the outside in. In essence, they are regions of space-time that eject matter and energy, but do not allow anything to enter. If black holes are cosmic traps, white holes are cosmic fountains. The concept of white holes arises from the solutions to Einstein's equations of general relativity. Specifically, the Schwarzschild metric, which describes a non-rotating black hole, has two distinct solutions, one representing a black hole and the other a white hole. These two entities are connected in mathematical theory, forming what is known as a maximally extended spacetime. However, while black holes have been observed and studied extensively, white holes remain purely hypothetical. One reason for the skepticism surrounding white holes is their apparent violation of the second law of thermodynamics. This fundamental principle states that the total entropy, or disorder, of a closed system must increase over time. Black holes comply with this law as they absorb matter and energy, increasing their entropy. White holes, by ejecting matter and energy, appear to decrease entropy, creating a paradox. This contradiction makes their existence highly unlikely according to conventional physics. Despite these challenges, white holes remain an intriguing concept in theoretical physics. Some researchers have suggested that white holes could be related to black holes through the phenomenon of time reversal. From this perspective, a white hole might be a black hole viewed in reverse, existing in a universe where the arrow of time points in the opposite direction. While this idea is purely speculative, it opens the door to fascinating possibilities about the nature of time and causality. White holes also find a natural home in discussions about the early universe. Some cosmological models propose that the Big Bang itself was a white hole, an event that expelled matter and energy into a newly forming space-time. In this view, the universe we inhabit might be the result of a white hole event, rather than a singularity in the traditional sense. While this interpretation is far from confirmed, it aligns with the notion of the Big Bang as an initial expansion rather than a collapse. Another speculative idea connects white holes to the concept of wormholes, or Einstein-Rosen bridges. These hypothetical structures link two separate regions of space-time, with one end functioning as a black hole and the other as a white hole. In such a scenario, matter entering the black hole could theoretically emerge from the white hole, providing a shortcut through space-time. While the stability of wormholes remains uncertain, they offer an intriguing framework for thinking about the relationship between black holes and white holes. The search for evidence of white holes has proven elusive. Unlike black holes, which can be detected by their gravitational influence and the radiation emitted by their accretion disks, white holes lack clear observational signatures. If they do exist, they would likely be transient phenomena, appearing and disappearing too quickly for current instruments to detect. Alternatively, they might exist in isolated regions of the universe, far removed from observable matter. Despite the lack of empirical evidence, the study of white holes continues to yield valuable insights into the nature of space-time and the limits of physical law. By challenging our understanding of entropy, causality, and the fabric of the universe, white holes push the boundaries of theoretical physics. Even if they remain hypothetical, they serve as a reminder that our universe is governed by principles that are often stranger and more complex than we can imagine. As we peer deeper into the cosmos and refine our understanding of its underlying laws, the question of white holes remains an open and fascinating mystery. Whether they are real phenomena or mathematical abstractions, they compel us to rethink the nature of creation, destruction, and the interconnectedness of all things. Could white holes be the missing piece in our quest to understand the universe? Or are they simply an illusion conjured by the equations of relativity? The answer lies in the uncharted territories of space-time, waiting to be discovered. Time dilation and singularities. What if time, the unyielding force that governs every aspect of our lives, could slow, stop, or even cease to exist altogether? Singularities, the mysterious cores of black holes, and potentially the origin point of the universe, force us to confront this mind-bending possibility. Time dilation, a phenomenon predicted by Einstein's general theory of relativity, is not merely a theoretical concept, but a reality shaped by the immense gravitational fields near singularities. Could this strange warping of time offer a deeper understanding of these enigmatic cosmic objects? To grasp the relationship between time dilation and singularities, we must first understand the interplay between gravity and time. In Einstein's framework, space-time is a unified fabric that curves in response to the presence of mass and energy. This curvature creates the phenomenon we perceive as gravity, and it also affects the passage of time. In regions of strong gravitational fields, such as near a black hole, time slows relative to areas of weaker gravity, a phenomenon known as gravitational time dilation. This effect has been confirmed by numerous experiments and observations. For instance, atomic clocks placed at different altitudes, where Earth's gravitational field is slightly weaker or stronger, measure time differently, with clocks at lower altitudes ticking more slowly. In the vicinity of a black hole, this effect becomes dramatically amplified. As an object approaches the event horizon, time for that object slows relative to a distant observer. To someone watching from afar, the object would appear to freeze at the edge of the event horizon, even as it continues to fall toward the singularity. But what happens inside the event horizon, where gravity grows even stronger and time dilation reaches extremes? For an object falling toward a singularity, the experience is radically different. From its own perspective, time flows normally, and the journey toward the singularity unfolds seamlessly. However, from the outside observer's viewpoint, the object never truly reaches the singularity. It remains suspended in time, an eternal shadow on the event horizon. This divergence in perspectives underscores the unique and counterintuitive nature of time near singularities. The concept of time, so fundamental to our understanding of reality, becomes malleable and subjective. Singularities represent the ultimate test of our theories of time, challenging us to reconcile these apparent contradictions with the laws of physics. The implications of time dilation near singularities extend beyond the theoretical. They raise profound questions about the nature of causality and the flow of time. Could singularities represent regions where time itself ceases to exist? If so, what does this mean for the information and matter that fall into them? These questions remain at the forefront of research into black holes and singularities, with scientists exploring the possibility that time inside a singularity might loop, fragment, or collapse entirely. Time dilation also plays a critical role in the search for answers to one of the most perplexing questions in physics. Could singularities be gateways to time travel? The extreme warping of space-time near singularities creates conditions that, in theory, might allow for closed time-like curves, paths through space-time that loop back on themselves. While these curves are purely speculative and fraught with paradoxes, they offer a tantalizing glimpse into the potential for singularities to unlock new dimensions of time and space. The study of time dilation near singularities is closely linked to the quest for a theory of quantum gravity. Classical general relativity describes time dilation in the macroscopic world, but it fails to account for the quantum effects that dominate at the smallest scales. Reconciling these two realms requires a deeper understanding of how time and gravity interact in the quantum domain. This is not merely a theoretical exercise. It has practical implications for understanding the early universe, where singularities may have played a pivotal role in shaping the cosmos. In addition to their scientific significance, the effects of time dilation near singularities have captured the imagination of storytellers and visionaries. From science fiction novels to blockbuster films, the idea of time slowing, stopping, or reversing near a black hole serves as a powerful narrative device, highlighting the profound interplay between science and creativity. These stories inspire us to explore the limits of what is possible, both in our understanding of physics and in our capacity for wonder. As we probe deeper into the mysteries of singularities and their relationship to time, one thing becomes clear. These cosmic objects challenge us to rethink the very nature of existence. Time, once thought to be an unchanging and universal constant, is revealed to be a dynamic and malleable force, shaped by the gravitational dance of the cosmos. Singularities, with their extreme environments and profound implications, remind us that the universe is far stranger and more intricate than we can imagine. The role of quantum mechanics. In the quest to unravel the mysteries of singularities, quantum mechanics emerges as a vital key, offering insights into realms where classical physics breaks down. Singularities, defined by infinite density and space-time curvature, push general relativity to its limits. Yet quantum mechanics, governing the behavior of the universe's smallest particles, might hold the answers. How do these two seemingly incompatible frameworks converge? And what role does quantum mechanics play in deciphering the enigmas of singularities? At the heart of this exploration lies the tension between general relativity and quantum mechanics. While general relativity excels at describing the large-scale structure of the universe, including the behavior of stars, galaxies, and black holes, quantum mechanics delves into the subatomic world, where particles and waves blur into probabilistic patterns. Singularities, as regions of infinite density, demand a synthesis of these two theories, a unified framework often referred to as quantum gravity. One of the most promising avenues in the search for quantum gravity is string theory, which posits that fundamental particles are not point-like, but rather one-dimensional strings vibrating at different frequencies. String theory has the potential to describe the extreme conditions near singularities, where space-time curvature becomes infinite. By replacing the classical notion of a singularity with a finite, stringy structure, this framework avoids the infinities that plague traditional descriptions. Another contender in the quest to unify quantum mechanics and general relativity is loop quantum gravity, a theory that reimagines space-time as a network of discrete loops. According to this perspective, space-time itself is quantized, much like the energy levels of an atom. This quantization eliminates the infinite densities predicted by classical relativity, replacing them with a finite, yet incredibly dense core. In this framework, singularities might not exist as physical entities, but instead mark the boundaries of our current understanding. Quantum mechanics also sheds light on the behavior of matter and energy near singularities. As particles approach a singularity, their wavelengths are stretched and compressed by the intense gravitational field. This stretching, known as gravitational redshift, alters the particle's energy and momentum, creating a cascade of quantum effects. At the event horizon, where gravity's pull is nearly insurmountable, quantum phenomena dominate, leading to a phenomenon known as Hawking radiation. Proposed by Stephen Hawking in the 1970s, Hawking radiation is a quantum mechanical effect that occurs near the event horizon of black holes. Virtual particle pairs, constantly forming and annihilating in the quantum vacuum, are separated by the immense gravitational field. One particle falls into the black hole, while the other escapes, creating the appearance of radiation emanating from the event horizon. Over time, this process causes the black hole to lose mass and energy, potentially leading to its eventual evaporation. This revolutionary idea not only integrates quantum mechanics into the study of black holes, but also raises profound questions about the nature of singularities and the fate of information. The intersection of quantum mechanics and singularities also brings us face to face with the infamous information paradox. When matter falls into a black hole, it carries information about its quantum state. According to classical physics, this information is irretrievably lost, violating the principles of quantum mechanics, which assert that information cannot be destroyed. The resolution of this paradox is a central challenge in modern physics, with potential solutions ranging from holographic principles to theories involving wormholes and multiverses. One compelling proposal to resolve the information paradox is the holographic principle, which suggests that all the information contained within a three-dimensional region of space-time can be encoded on its two-dimensional boundary. This concept, inspired by the mathematics of black hole thermodynamics, implies that singularities might not be the mysterious points we imagine, but rather projections of information encoded at the event horizon. If true, this principle could revolutionize our understanding of black holes, singularities, and the fabric of spacetime itself. Quantum mechanics also offers a glimpse into the possibility of singularities as portals to other dimensions or universes. Theoretical constructs like Einstein-Rosen bridges or wormholes suggest that singularities might connect disparate regions of spacetime. While these ideas remain speculative, they challenge our notions of causality and locality, hinting at a universe far richer and more interconnected than we currently comprehend. As we probe deeper into the quantum realm, the study of singularities becomes increasingly tied to cutting-edge technology. Advanced simulations and experiments at facilities like the Large Hadron Collider provide insights into high-energy physics, mirroring the extreme conditions near singularities. Meanwhile, developments in quantum computing offer the potential to model these phenomena with unprecedented precision, accelerating our quest to understand the universe's most enigmatic regions. Quantum mechanics, with its principles of uncertainty, superposition, and entanglement, invites us to rethink the very foundations of reality. Singularities, once seen as impenetrable boundaries, become gateways to deeper truths, places where the classical and quantum worlds converge in a dance of infinite complexity. The role of quantum mechanics in decoding singularities is not merely a scientific endeavor. It is a journey into the heart of existence, where the mysteries of the cosmos and the nature of reality intertwine. Spaghettification, the gruesome side of black holes. If there is one term in astrophysics that blends scientific precision with visceral imagery, it is spaghettification. This phenomenon, where objects are stretched into elongated strands as they approach a black hole, epitomizes the extreme forces at play near a singularity. But what causes this cosmic distortion? And could anything, whether a spacecraft, a planet, or even a human, survive such a journey? To understand spaghettification, we must first explore the gravitational gradients that define the regions near a black hole. Gravity weakens with distance, but in the vicinity of a black hole, this change occurs with unparalleled intensity. This is due to the curvature of space-time, which becomes infinitely steep as one approaches the event horizon. The result is a dramatic difference in gravitational pull between 2 points on the same object, a phenomenon known as tidal forces. Imagine an object, such as a spaceship, venturing too close to a black hole. The gravitational pull on the side of the spaceship closer to the black hole is significantly stronger than on the farther side. This difference creates a stretching force along the object's length while simultaneously compressing it in other dimensions. The result is spaghettification, a grotesque elongation that reduces even the sturdiest materials to atomic strings. For black holes of stellar mass, spaghettification occurs well before reaching the event horizon. The tidal forces become overwhelming long before the boundary is crossed, making the experience lethal for any object or organism. However, in the case of supermassive black holes, which have event horizons spanning millions of kilometers, the tidal forces near the event horizon are relatively mild. In these scenarios, an object could theoretically pass through the event horizon intact, only to face spaghettification closer to the singularity. The process of spaghettification is not just a violent ordeal. It is also a journey into the unknown. As an object falls deeper into the black hole, the stretching continues until it surpasses even the atomic level. Electrons are stripped from nuclei, and subatomic particles are scattered. This disintegration represents not just the destruction of form, but a transformation of matter into its most fundamental constituents. What happens to this matter after spaghettification? From the perspective of an external observer, the object appears to freeze in time as it approaches the event horizon. This is due to gravitational time dilation, where the intense gravity slows the passage of time near the black hole. To the falling object, however, time flows normally, and the descent toward the singularity is inevitable. The fate of matter that reaches the singularity is one of the most profound mysteries in astrophysics. Does it merge into the singularity's infinite density, becoming part of the enigmatic core? Or is it somehow preserved, its information encoded in the black hole's quantum state? The answer to these questions has implications for our understanding of black holes, singularities, and the fundamental nature of matter and energy. Spaghettification is not limited to the theoretical realm. Observations of tidal disruption events, where stars venture too close to black holes and are torn apart, provide real-world evidence of this phenomenon. When a star undergoes spaghettification, its material is stretched into long streams that spiral toward the black hole, forming an accretion disk. The intense heat generated by friction within the disk produces X-rays and other high-energy emissions, creating some of the most luminous events in the universe. These tidal disruption events also offer a unique window into the study of black holes. By analyzing the light and energy emitted during these events, astronomers can infer the properties of the black hole, such as its mass and spin. This provides valuable insights into the behavior of black holes and the extreme physics of their surroundings. For humans, the idea of spaghettification is both terrifying and fascinating. While the prospect of being stretched into oblivion is far from appealing, it underscores the sheer power and unpredictability of black holes. Could a sufficiently advanced civilization develop technology to resist spaghettification and explore these regions safely? The concept might seem far-fetched, but it fuels the imagination and inspires bold visions of future exploration. Beyond its scientific implications, spaghettification serves as a reminder of the universe's extremes. It is a testament to the relentless forces at play in the cosmos, where beauty and destruction coexist in an intricate dance. Singularities and their spaghettifying grip push the boundaries of what we can comprehend, challenging us to delve deeper into the mysteries of space and time. As we continue to study black holes and the singularities they harbor, spaghettification stands as both a symbol of the dangers and a gateway to discovery. Whether as a theoretical construct or a real-world phenomenon, it invites us to confront the unimaginable and embrace the unknown. Wormholes, bridging singularities. What if singularities were not the ultimate dead ends of space-time, but gateways to new realms? Wormholes, theoretical constructs predicted by Einstein's general theory of relativity, offer a tantalizing possibility, a bridge between two separate points in space-time. These enigmatic pathways, sometimes called Einstein-Rosen bridges, have captured the imaginations of physicists and science fiction enthusiasts alike. But are wormholes the stuff of fantasy, or could they exist as real phenomena hidden in the fabric of the cosmos? At their core, wormholes are solutions to Einstein's field equations, describing a tunnel-like structure connecting two distant regions of space-time. Imagine bending a piece of paper to bring 2 points closer together, then punching a hole through the paper. This is a simplified analogy for how a wormhole could work, potentially allowing travel across vast cosmic distances, or even between different universes, in a fraction of the time it would take to traverse them conventionally. The concept of wormholes dates back to 1935, when Albert Einstein and Nathan Rosen explored the possibility of connecting two black holes via a space-time bridge. Their solution, now known as the Einstein-Rosen bridge, described a symmetrical wormhole with black holes at either end. However, this early model was inherently unstable, prone to collapse almost instantly after forming. The stability of wormholes remains one of the greatest challenges to their existence. For a wormhole to remain open, it would require the presence of exotic matter, hypothetical material with negative energy density and unusual properties, such as exerting a repulsive gravitational force. While exotic matter has not been observed, quantum theories suggest it might arise under certain conditions, such as within the Casimir effect, where negative energy is created between closely spaced surfaces. If wormholes could be stabilized, their implications would be profound. They could serve as shortcuts for interstellar travel, allowing humans to traverse the galaxy or even explore other universes. Theoretical physicist Kip Thorne popularized the idea of traversable wormholes, which could enable time travel by creating pathways through space-time loops. This raises intriguing possibilities but also paradoxes, such as the grandfather paradox, where traveling back in time to alter the past could create inconsistencies in causality. Wormholes are not confined to science fiction. They have a basis in serious scientific inquiry. Quantum mechanics introduces the concept of quantum foam, a chaotic, fluctuating fabric of space-time at the smallest scales. Some physicists speculate that wormholes might naturally form and vanish within this foam, existing only for infinitesimal moments. If such microscopic wormholes could be stabilized and expanded, they might provide a pathway to explore the quantum realm or connect distant regions of the universe. The search for observational evidence of wormholes has proven elusive. While black holes have been detected through their gravitational effects and the radiation emitted by their accretion disks, wormholes remain hidden, if they exist at all. Some theories suggest that wormholes might mimic the appearance of black holes, making them indistinguishable from their more familiar counterparts. Alternatively, the mouths of wormholes might emit distinctive radiation patterns or create gravitational lensing effects that could be detected with advanced instruments. The relationship between wormholes and singularities is another area of active exploration. Some models propose that singularities at the centers of black holes could serve as entry points for wormholes. In such scenarios, the extreme conditions near singularities might create the necessary environment for a wormhole to form. However, the immense tidal forces and spaghettification associated with singularities pose significant challenges for any matter attempting to pass through. Wormholes also intersect with broader cosmological theories, such as the multiverse hypothesis. If multiple universes exist, wormholes could provide a means of traversing them, linking our cosmos to parallel realities. This idea, while speculative, aligns with certain interpretations of quantum mechanics and string theory, suggesting a universe far richer and more interconnected than we currently understand. Despite the allure of wormholes, they remain highly theoretical. The mathematical models that describe them are fraught with uncertainties, and the lack of empirical evidence leaves their existence an open question. Nevertheless, their study pushes the boundaries of physics, inspiring new ways of thinking about space-time, gravity, and the nature of the universe. As we continue to explore the cosmos, wormholes serve as a powerful symbol of possibility. Whether as a practical tool for interstellar travel or a conceptual framework for understanding the universe's hidden dimensions, they invite us to dream beyond the limits of our current knowledge. Singularities, once seen as inescapable traps, might instead be gateways to unimaginable realms, where the laws of physics take on new and wondrous forms. Singularities in fiction and pop culture. Singularities, with their mind-bending physics and connections to the most extreme phenomena in the universe, have captivated the imaginations of writers, filmmakers, and creators for decades. From black holes swallowing spaceships to wormholes opening gateways to distant galaxies, these cosmic enigmas have become a staple in popular culture. But how accurately do these portrayals align with scientific understanding, and what makes singularities such a compelling narrative device? The allure of singularities in fiction lies in their dual nature. They are both scientifically grounded and deeply mysterious. Singularities are the ultimate unknown, places where the laws of physics break down and anything seems possible. This blend of factual basis and creative freedom provides fertile ground for storytelling, allowing writers to explore themes of survival, exploration, and the limits of human knowledge. One of the earliest and most iconic representations of singularities in popular culture is the black hole. These celestial objects first captured the public imagination in the mid-20th century, as advances in astrophysics began to reveal their theoretical underpinnings. The 1979 film The Black Hole brought this concept to the big screen, depicting a crew of explorers venturing perilously close to a massive black hole. While the film took liberties with the science, it highlighted the intense gravitational pull and eerie inescapability associated with these objects. Modern portrayals have continued to push the boundaries of imagination while integrating more accurate science. Christopher Nolan's Interstellar is a prime example, featuring a meticulously crafted depiction of a supermassive black hole named Gargantua. Working with physicist Kip Thorne, the filmmakers created visual effects based on real equations, showcasing the warping of light and space-time around the event horizon. This attention to detail brought the science of singularities to mainstream audiences, sparking renewed interest in their study. Singularities also play a central role in stories involving wormholes and time travel. In Star Trek, wormholes are often used as shortcuts through space, connecting distant regions of the galaxy. Similarly, the film Contact, based on Carl Sagan's novel, explores the possibility of interstellar travel via a wormhole created by advanced extraterrestrial civilizations. While these portrayals take significant creative liberties, they are rooted in the theoretical framework of Einstein-Rosen bridges, making them plausible within the bounds of speculative science. Time travel narratives frequently invoke singularities as a mechanism for bending or breaking the flow of time. The concept of closed time-like curves, loops in space-time that could allow a traveler to revisit the past, appears in numerous stories from Doctor Who to Avengers Endgame. While these scenarios often ignore the practical challenges, such as the immense energy required to stabilize a wormhole, they illustrate the narrative potential of singularities as tools for exploring causality and paradox. Beyond film and television, singularities have inspired countless works of literature. Arthur C. Clarke's 2001 A Space Odyssey delves into the transformative potential of black holes, imagining them as gateways to higher dimensions and advanced forms of consciousness. Similarly, in Greg Egan's novel Diaspora, singularities serve as a focal point for exploring the nature of existence and the limits of human understanding. These stories use singularities not just as plot devices, but as metaphors for the unknown, challenging readers to confront the mysteries of the cosmos. The fascination with singularities extends to video games, where they often serve as dramatic settings or powerful forces. Titles like Mass Effect incorporate black holes and wormholes into their world building, using them to explain faster-than-light travel and the dangers of unrestrained technological advancement. Meanwhile, games like Elite Dangerous allow players to explore the environments around real-world black holes, blending scientific accuracy with interactive storytelling. Despite their widespread presence in fiction, singularities are often misunderstood or oversimplified in popular culture. Many portrayals ignore the complexities of spaghettification, time dilation, and Hawking radiation, favoring spectacle over accuracy. For instance, the idea of a spaceship surviving a journey into a black hole often defies the extreme tidal forces that would tear it apart long before reaching the event horizon. Similarly, the depiction of wormholes as stable and traversable overlooks the theoretical requirement for exotic matter, which remains purely hypothetical. Yet these simplifications are not necessarily a detriment. By capturing the imagination of audiences, these stories inspire curiosity and interest in the real science behind singularities. Popular culture serves as a gateway to learning, encouraging people to delve deeper into astrophysics and cosmology. Films, books, and games often spark the initial fascination that leads future scientists to explore the mysteries of the universe. Singularities also hold a unique, symbolic power in storytelling. They represent the ultimate challenge to human understanding, embodying the idea of confronting the unknown. Whether as portals to other worlds, sources of unimaginable power, or harbingers of destruction, singularities compel characters and audiences to grapple with their limits and push beyond them. This resonance with universal themes ensures that singularities will remain a fixture in popular culture for generations to come. As scientific understanding of singularities evolves, so too will their representation in fiction. Advances in imaging technologies, such as the Event Horizon Telescope, have already transformed our understanding of black holes, providing unprecedented visual evidence of their existence. These developments will undoubtedly influence future portrayals, grounding them in even greater scientific realism while preserving their sense of wonder and mystery. Singularities are more than just a scientific curiosity. They are a narrative goldmine, offering endless opportunities for exploration, innovation, and storytelling. They bridge the gap between the known and the unknown, inspiring us to dream about what lies beyond the horizon of our understanding. Cosmic mysteries, naked singularities. When we think of singularities, they are often hidden behind the event horizons of black holes, shrouded from the view of the outside universe. But what if some singularities were naked, exposed for all to see? This tantalizing possibility challenges our understanding of cosmic order and raises profound questions about the nature of space-time and gravity. Naked singularities, theoretical objects without the cloaking of an event horizon, occupy a controversial and fascinating niche in astrophysics. Could they exist? And if so, what would they reveal about the universe? To understand the concept of a naked singularity, we must first revisit the role of the event horizon in a black hole. The event horizon acts as a one-way boundary. Nothing can escape from within it, not even light. This boundary ensures that the singularity at the black hole's core remains hidden, preserving the structure of space-time as described by general relativity. Naked singularities, on the other hand, lack this protective shroud. Their gravitational pull is not strong enough to form an event horizon, leaving the singularity exposed to the universe. The existence of naked singularities would violate the cosmic censorship conjecture, a principle proposed by physicist Roger Penrose in 1969. This conjecture asserts that singularities are always hidden behind event horizons, ensuring that the universe remains orderly and predictable on a macroscopic scale. If naked singularities were to exist, they would expose the raw infinities of space-time, potentially causing the breakdown of physical laws as we understand them. What might lead to the formation of a naked singularity? Some models suggest that the conditions required for their creation could arise in extreme astrophysical scenarios, such as the collapse of a massive star with insufficient angular momentum to form a black hole. Alternatively, certain solutions to Einstein's equations, such as those describing Kerr black holes with high spin rates, suggest that naked singularities might form under specific configurations. These scenarios remain purely theoretical, but they highlight the delicate interplay between mass, spin, and gravity in shaping the cosmos. The prospect of observing a naked singularity is both thrilling and daunting. If such an object exists, it would provide a unique laboratory for studying the extremes of physics, offering direct access to the singularity itself. The curvature of space-time near a naked singularity would be so intense that it could generate phenomena unlike anything we have ever observed, such as the bending of light into intricate and chaotic patterns. These effects, if detected, could provide invaluable insights into the nature of gravity and the structure of space-time. However, the exposure of a naked singularity also raises troubling questions. Without the event horizon to shield the singularity, the infinite density and curvature would be laid bare, potentially destabilizing the surrounding region of space-time. This could lead to unpredictable effects, such as the distortion of causality or the emergence of closed time-like curves, loops in time that challenge our understanding of cause and effect. Despite their theoretical intrigue, naked singularities have yet to be observed. The search for these elusive objects involves studying extreme astrophysical environments, such as regions of space where black holes may be forming or merging. Advanced observational tools, such as gravitational wave detectors and high-resolution telescopes, provide the means to probe these phenomena with unprecedented precision. While no definitive evidence for naked singularities has been found, the possibility remains an active area of research. The debate over naked singularities extends beyond physics to philosophical questions about the nature of the universe. If cosmic censorship fails and naked singularities can exist, what does this imply about the predictability of nature? Could the universe be fundamentally chaotic, with regions where the laws of physics break down completely? These questions challenge the deterministic view of the cosmos and open the door to new ways of thinking about reality. One intriguing implication of naked singularities is their potential role in testing theories of quantum gravity. The conditions near a naked singularity would combine the extreme curvature of general relativity with the quantum effects that dominate at small scales, providing a natural setting for exploring the intersection of these two realms. Insights gained from studying naked singularities could guide the development of a unified theory, bringing us closer to understanding the fundamental workings of the universe. In popular culture, the idea of naked singularities has captured the imagination of creators and audiences alike. These objects often appear as sources of immense power or portals to other dimensions, serving as dramatic focal points in stories of cosmic adventure. While these portrayals take creative liberties, they reflect the awe and curiosity that naked singularities inspire in both scientists and the public. As we continue to explore the universe, the question of naked singularities remains one of the most compelling mysteries in astrophysics. Whether they exist or not, their study challenges us to confront the boundaries of knowledge and to embrace the complexities of a universe that is far stranger and more intricate than we can imagine. Hawking radiation, the evaporation of black holes. Black holes, long considered inescapable cosmic prisons, hold an extraordinary secret. Far from being eternal, they can gradually lose mass and energy, a process driven by a phenomenon known as Hawking radiation. First proposed by physicist Stephen Hawking in the 1970s, this groundbreaking theory challenged the conventional understanding of black holes as permanent and unchanging. But how does Hawking radiation work, and what does it reveal about the deeper nature of singularities and the universe? At the heart of Hawking radiation lies the strange and counterintuitive world of quantum mechanics. In the vacuum of space, particles and antiparticles are constantly being created and annihilated in pairs. This fleeting activity is a consequence of quantum fluctuations, which occur even in the absence of matter or energy. Near the event horizon of a black hole, however, this process takes on a unique character. When a particle-antiparticle pair forms near the event horizon, the immense gravitational pull of the black hole can separate the two particles before they annihilate each other. One particle falls into the black hole, while the other escapes into space. To an external observer, it appears as though the black hole is emitting radiation, a phenomenon we now call Hawking radiation. Over time, this radiation causes the black hole to lose energy, leading to a gradual reduction in its mass. The implications of Hawking radiation are profound. For one, it suggests that black holes are not truly black. Instead, they emit faint thermal radiation, with a temperature inversely proportional to their mass. This means that smaller black holes radiate more intensely, while supermassive black holes lose energy at an almost imperceptible rate. Over vast timescales, however, even the largest black holes are predicted to evaporate entirely, leaving behind a universe devoid of these once dominant cosmic entities. The process of black hole evaporation raises fascinating questions about the ultimate fate of matter and information. When a black hole forms, it traps not only mass, but also the information encoded in the matter it consumes. According to classical physics, this information should be lost forever, as nothing can escape the event horizon. However, the laws of quantum mechanics forbid the destruction of information, creating a paradox that has puzzled physicists for decades. This information paradox is one of the most significant challenges in theoretical physics. Does Hawking radiation carry information about the matter that fell into the black hole, or is the information irretrievably lost? Various theories attempt to resolve this paradox. Some suggest that the information is encoded in subtle correlations within the Hawking radiation itself, while others propose that it might be preserved on the event horizon, as described by the holographic principle. The holographic principle, inspired by black hole thermodynamics, posits that the information content of a three-dimensional region of space can be encoded on its two-dimensional boundary. In the context of black holes, this means that the event horizon might serve as a screen, storing all the information about the objects that have fallen in. If true, this principle could revolutionize our understanding of black holes and the fundamental nature of space-time. Hawking radiation also has implications for the study of singularities. As a black hole evaporates, its event horizon shrinks, and the singularity at its core becomes increasingly exposed. In the final stages of evaporation, the black hole's mass approaches zero, leading to an intense burst of radiation, a phenomenon sometimes referred to as a black hole explosion. What happens to the singularity in these moments remains an open question. Does it vanish along with the black hole, or does it leave behind a remnant, such as a stable quantum object? The study of Hawking radiation bridges the gap between quantum mechanics and general relativity, offering a glimpse into the elusive realm of quantum gravity. By examining the behavior of black holes at the smallest scales, physicists hope to uncover the underlying principles that govern the interplay between gravity and quantum effects. This research not only deepens our understanding of black holes, but also has broader implications for cosmology, particle physics, and the origins of the universe. Observationally, detecting Hawking radiation remains an enormous challenge. The radiation emitted by astrophysical black holes is exceedingly faint, dwarfed by other sources of cosmic radiation. However, experimental efforts to simulate black hole analogs in laboratory settings have provided intriguing insights. For example, researchers have created systems that mimic event horizons using flowing fluids and other materials, allowing them to study the properties of Hawking-like radiation in controlled environments. Hawking radiation has also captured the imagination of the public, inspiring a new wave of interest in black holes and their mysteries. The concept of black holes evaporating over time, eventually disappearing altogether, challenges our notions of permanence and change. It reminds us that even the most enduring structures in the universe are subject to the inexorable flow of time and the laws of physics. As we continue to explore the implications of Hawking radiation, we are reminded of the profound interconnectedness of the cosmos. This phenomenon, rooted in the interplay of gravity and quantum mechanics, offers a window into the deepest layers of reality. It invites us to rethink our understanding of singularities, black holes, and the ultimate fate of the universe. Singularities as windows into higher dimensions. The concept of singularities often conjures images of points where physical laws break down. But what if these enigmatic entities serve a greater purpose? Could singularities be more than mere endpoints in space-time, perhaps gateways to higher dimensions or alternate realms of existence? This idea, while deeply speculative, has captured the imaginations of physicists and cosmologists alike. By exploring the potential of singularities as windows into higher dimensions, we embark on a journey into the most uncharted territories of the universe. To understand the connection between singularities and higher dimensions, we must first consider the fabric of spacetime itself. In our everyday experience, spacetime consists of 3 spatial dimensions and 1 temporal dimension. However, theories such as string theory propose the existence of additional dimensions beyond these familiar 4. These hidden dimensions, compactified and curled up at minuscule scales, may hold the key to understanding the behavior of singularities and the fundamental structure of the cosmos. Singularities, with their extreme densities and space-time curvatures, create conditions that defy conventional physics. Near a singularity, the gravitational forces are so intense that they compress matter and energy to infinitesimal scales. In such an environment, the effects of higher dimensions, if they exist, become significant. The singularity could act as a portal or focal point where these dimensions intersect with our observable universe. One compelling framework for exploring this idea is the multiverse hypothesis. According to this concept, our universe is just one of many, each with its own set of physical laws and dimensions. Singularities, particularly those within black holes, might serve as bridges between these universes. In this scenario, matter and energy falling into a black hole in one universe could emerge in another, forming the seeds of a new cosmos. This idea aligns with the notion of a white hole, the theoretical counterpart to a black hole, which expels matter and energy rather than consuming it. The possibility of higher dimensions also intersects with the concept of wormholes. These hypothetical structures, which connect 2 separate regions of spacetime, could be stabilized by the presence of additional dimensions. Singularities might serve as the entry or exit points of these wormholes, creating pathways that bypass the limitations of our 3-dimensional perspective. Such connections could allow for faster-than-light travel, interdimensional exploration, or even communication across vast cosmic distances. Higher dimensional theories offer intriguing explanations for the behavior of singularities. In string theory, for example, the building blocks of reality are not point-like particles but tiny vibrating strings. These strings interact within a space-time framework that includes additional dimensions, such as the 6 compactified dimensions proposed by the Calabi-Yau manifolds. At the singularity, the geometry of these hidden dimensions could influence the behavior of matter and energy, potentially resolving the infinities predicted by classical physics. Another theoretical approach involves brane cosmology, which suggests that our universe is a 3-dimensional brane embedded within a higher dimensional bulk. Singularities could represent points where the brane interacts with the bulk, allowing for the exchange of information or energy between dimensions. This perspective has profound implications for understanding dark matter, gravity, and the origins of the universe itself. Observational evidence for higher dimensions remains elusive, but researchers continue to explore indirect clues. Experiments with particle accelerators, such as the Large Hadron Collider, seek to uncover signs of extra dimensions by studying high-energy collisions. Meanwhile, studies of gravitational waves and black hole mergers offer insights into the extreme environments where higher dimensional effects might become apparent. Singularities as windows into higher dimensions also raise philosophical questions about the nature of reality. If these hidden realms exist, what role do they play in shaping our universe? Are they merely mathematical abstractions, or do they have tangible effects on our everyday lives? Exploring these questions challenges our perceptions of space, time, and existence, inviting us to consider a universe far richer and more intricate than we currently imagine. In popular culture, the idea of singularities as gateways to other dimensions has inspired countless stories and visualizations. Films like Interstellar and The Black Hole depict black holes as portals to uncharted realms, blending scientific speculation with artistic creativity. These portrayals, while often dramatized, reflect the enduring fascination with the possibility of higher dimensions and the role singularities might play in accessing them. As we delve deeper into the mysteries of singularities and higher dimensions, we are reminded of the interconnectedness of science and imagination. Singularities challenge us to confront the limits of our knowledge and to seek answers in the most extreme and unfamiliar corners of the universe. Whether they lead to higher dimensions, alternate realities, or entirely new understandings of space-time, singularities stand as testaments to the boundless potential of human curiosity. Gravitational waves and their relation to singularities. Ripples in space-time, moving at the speed of light, carry echoes of the universe's most cataclysmic events. These are gravitational waves, one of the most profound discoveries in modern physics. First predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity, gravitational waves remained undetected for a century until their groundbreaking observation in 2015. But what do these waves reveal about singularities? And how are they connected to the mysterious cores of black holes? Gravitational waves are produced by the acceleration of massive objects, particularly during violent cosmic events such as black hole mergers, neutron-star collisions, and supernovae. These waves propagate outward from their source, distorting space-time in a manner similar to ripples spreading across a pond. For singularities, which lie at the hearts of black holes, these waves serve as messengers, carrying information about their formation, dynamics, and interactions. The first direct detection of gravitational waves, achieved by the LIGO Observatory, came from the merger of two black holes. This monumental event provided not only confirmation of gravitational waves, but also a new method for studying singularities. When black holes merge, their singularities coalesce, releasing vast amounts of energy in the form of gravitational waves. By analyzing the frequency and amplitude of these waves, scientists can infer the masses, spins, and orbital dynamics of the merging black holes. One of the most intriguing aspects of gravitational waves is their ability to probe regions of the universe that are otherwise inaccessible. Singularities, hidden behind the event horizons of black holes, emit no light or electromagnetic radiation. Traditional telescopes cannot observe them directly. However, gravitational waves can escape from the regions surrounding singularities, offering a unique glimpse into their behavior and properties. This makes gravitational wave astronomy a powerful tool for studying these enigmatic objects. The relationship between gravitational waves and singularities extends to their role in testing the limits of general relativity. Einstein's theory has been remarkably successful in describing gravity on large scales, but singularities represent points where the equations break down. By studying the gravitational waves produced during extreme events, scientists can test the predictions of general relativity under conditions of intense gravity and curvature. Deviations from these predictions could hint at new physics or the need for a more comprehensive theory, such as quantum gravity. Gravitational waves also provide insights into the environments around singularities. For example, the waves emitted during black hole mergers carry information about the warped space-time near the event horizon. These ring-down signals, observed in the aftermath of a merger, reveal the properties of the resulting black hole, including its mass, spin, and stability. By studying these signals in detail, researchers can explore the dynamics of space-time near a singularity and test the no-hair theorem, which states that black holes are fully described by their mass, charge, and spin. The detection of gravitational waves from neutron-star mergers has expanded the scope of singularity research. When neutron stars collide, they often form a black hole, creating a singularity in the process. The gravitational waves emitted during these events, combined with electromagnetic signals such as gamma-ray bursts, offer a multi-messenger approach to studying singularities. This synergy between gravitational wave and traditional astronomy enhances our understanding of the processes that lead to the formation of black holes and their singularities. One of the most exciting prospects for gravitational wave research is the potential discovery of primordial black holes. These hypothetical objects, formed in the early universe, could harbor singularities that predate the formation of stars and galaxies. Detecting gravitational waves from primordial black hole mergers would provide direct evidence for their existence and offer clues about the conditions of the universe shortly after the Big Bang. Such discoveries could revolutionize our understanding of singularities and their role in cosmic evolution. As gravitational wave observatories improve, the field of singularity research is poised for transformative discoveries. Next-generation detectors, such as LISA, Laser Interferometer Space Antenna, will operate in space, offering unprecedented sensitivity to gravitational waves from supermassive black hole mergers and other extreme events. These observations will allow scientists to study singularities on scales that were previously unimaginable, opening new windows into the nature of space-time and gravity. The relationship between gravitational waves and singularities is not just a scientific inquiry. It is a testament to human ingenuity and the power of exploration. These waves, traveling across billions of light years, carry the stories of singularities that have shaped the universe. By decoding their signals, we are piecing together a cosmic narrative that spans from the smallest scales of space-time to the largest structures in the cosmos. Gravitational waves have transformed singularities from abstract mathematical concepts into tangible objects of study. They connect the theoretical with the observable, bridging the gap between our understanding of physics and the mysteries of the universe. As we continue to listen to the echoes of singularities through gravitational waves, we take another step closer to unraveling the secrets of existence itself. The fate of information in singularities. The universe, it seems, is reluctant to let go of its secrets. When matter falls into a black hole, it carries with it an intricate blueprint of information about its composition, quantum state, and arrangement. But what happens to this information when it crosses the event horizon and approaches the singularity? Does it vanish into oblivion, defying the principles of quantum mechanics? Or is it somehow preserved? The fate of information in singularities is one of the most profound and contentious questions in modern physics, touching on the very foundations of reality. At the core of this debate is the black hole information paradox, a conflict between general relativity and quantum mechanics. General relativity suggests that anything falling into a black hole is lost forever, including the information it contains. Once matter reaches the singularity, it is compressed to infinite density, effectively erasing all traces of its original structure. However, quantum mechanics asserts that information cannot be destroyed. This principle, known as unitarity, is a cornerstone of quantum theory, ensuring that the past and future of a system are connected in a predictable way. Stephen Hawking's groundbreaking work on black hole thermodynamics in the 1970s introduced a new layer of complexity to this paradox. Hawking demonstrated that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. This Hawking radiation allows black holes to lose mass and energy over time, eventually leading to their evaporation. If the black hole disappears completely, what happens to the information it once contained? Does it escape with the radiation, or is it lost forever? One possible resolution to the information paradox lies in the holographic principle, a revolutionary idea that emerged from the study of black hole entropy. Proposed by Gerard T. Hooft and later expanded by Leonard Susskind, the holographic principle suggests that all the information about a three-dimensional region of space can be encoded on its two-dimensional boundary. In the context of black holes, this implies that the event horizon, a surface of no return, might act as a hologram, storing all the information about the matter and energy that falls into the black hole. When the black hole emits Hawking radiation, the encoded information could gradually leak out, preserving unitarity. The holographic principle finds support in string theory, where it aligns with the concept of AD/CFT correspondence, anti de Sitter/conformal field theory correspondence. This duality posits that a gravitational system in a higher dimensional space-time can be fully described by a quantum theory in lower dimensions. Applied to black holes, it suggests that the information within a singularity might be encoded in the surrounding space-time, potentially making it accessible in some form. Another intriguing approach to resolving the information paradox involves the idea of quantum entanglement. In quantum mechanics, particles that have interacted remain connected, such that the state of one particle is dependent on the state of the other, no matter the distance between them. This phenomenon could allow information about the interior of a black hole to remain entangled with the Hawking radiation it emits. If true, the information might not be destroyed, but rather redistributed across the radiation field. The quest to understand the fate of information has led to bold and speculative theories, including the possibility of firewalls. In this scenario, the event horizon of a black hole is not a smooth boundary, but a searing wall of high-energy particles. As matter crosses this firewall, the information it carries is destroyed, providing a radical but controversial solution to the paradox. However, firewalls challenge the principle of general relativity, which predicts that an observer falling into a black hole would experience no sudden effects at the event horizon, a concept known as the no-drama principle. One of the most intriguing ideas is that information could escape black holes through quantum tunneling or wormholes. These pathways, while purely theoretical, suggest that black holes might connect to other regions of space-time or even alternate universes. In such a case, the information would not be lost but rather transferred to a different domain, beyond the reach of our current observational capabilities. Observationally, the fate of information in black holes remains an enigma. Instruments like the Event Horizon Telescope and gravitational wave observatories provide indirect glimpses into the environments near black holes, but they cannot yet probe the singularity itself. However, future advancements in quantum computing and experimental physics may offer new ways to simulate and test these ideas, shedding light on the ultimate destiny of information in the universe. Philosophically, the information paradox challenges our understanding of reality. If information is truly lost in singularities, it would represent a fundamental break in the predictability of nature. Conversely, if it is preserved, it would reinforce the interconnectedness of the cosmos, where no detail is ever truly erased. This debate touches on questions of determinism, causality, and the very fabric of existence. As we grapple with the fate of information in singularities, we are reminded of the interplay between the known and the unknown. The paradox forces us to confront the limits of our knowledge and to seek answers in the most extreme and mysterious corners of the universe. Whether information survives the journey into a black hole or vanishes into the singularity, the quest to understand its fate continues to push the boundaries of science and imagination. The future of singularity research. The study of singularities stands at the crossroads of some of the most fundamental questions in physics, cosmology, and mathematics. These enigmatic regions, where space-time and the laws of physics break down, challenge our understanding of the universe and compel us to seek answers in uncharted realms. As technology advances and theoretical frameworks evolve, the future of singularity research promises to be as transformative as it is profound. What breakthroughs lie ahead, and how might they reshape our view of reality? One of the most promising developments in singularity research is the continued refinement of observational technologies. Instruments like the Event Horizon Telescope, EHT, which captured the first direct image of a black hole in 2019, are ushering in a new era of black hole studies. By combining data from multiple observatories across the globe, the EHT creates a virtual telescope the size of Earth, capable of resolving details at the edges of black hole event horizons. Future iterations of this technology will provide even sharper images, allowing scientists to study the dynamics near singularities with unprecedented clarity. Gravitational wave astronomy is another frontier poised to revolutionize singularity research. The detection of gravitational waves by observatories like LIGO and Virgo has already provided invaluable insights into black hole mergers and the behavior of extreme gravitational systems. Next-generation detectors, such as the space-based LISA laser interferometer space antenna, will expand the range of detectable frequencies, enabling the study of supermassive black hole mergers and primordial black holes. These observations will offer a deeper understanding of singularity formation and the role these objects play in shaping the cosmos. Theoretical advances in quantum gravity remain at the heart of singularity research. Reconciling general relativity and quantum mechanics is essential for understanding the extreme conditions near singularities, where both gravitational and quantum effects are significant. Approaches such as string theory and loop quantum gravity offer promising frameworks, but they require further development and experimental validation. Breakthroughs in these areas could yield a unified theory of quantum gravity, resolving long-standing paradoxes and providing a comprehensive description of singularities. Artificial intelligence, AI, and machine learning are emerging as powerful tools in the study of singularities. These technologies excel at analyzing vast data sets, identifying patterns, and simulating complex systems. In astrophysics, AI algorithms are already being used to classify gravitational wave signals, model accretion disks, and predict the behavior of black holes. As AI continues to advance, it will play a crucial role in exploring the intricate dynamics of singularities and uncovering new phenomena. The search for exotic singularities, such as naked singularities and white holes, represents another exciting avenue of research. Naked singularities, if they exist, would provide direct access to regions where space-time curvature becomes infinite, offering unparalleled opportunities to test the limits of physical laws. Similarly, white holes, as theoretical counterparts to black holes, could shed light on the interplay between gravity and entropy. While these objects remain hypothetical, their study challenges our understanding of cosmic structure and opens the door to innovative ideas. Cosmology, too, is deeply intertwined with singularity research. The Big Bang, often described as a singularity, marks the beginning of our universe and raises profound questions about its origins. Was the Big Bang truly a singularity, or does it represent a transition from a prior state? Advances in observational cosmology, including the study of the cosmic microwave background and large-scale structure, will help answer these questions. Additionally, the search for primordial black holes and their potential role in seeding galaxy formation or explaining dark matter will provide new perspectives on singularities and their cosmic significance. Philosophical and ethical considerations will also shape the future of singularity research. As we probe deeper into the mysteries of black holes and space-time, we must grapple with the implications of our discoveries. Could understanding singularities lead to technological advancements with unforeseen consequences, such as the manipulation of space-time or the creation of artificial black holes? These questions demand careful thought and a commitment to responsible exploration. Public engagement and interdisciplinary collaboration will be essential for advancing singularity research. By fostering partnerships between physicists, mathematicians, computer scientists, and philosophers, we can approach these complex problems from multiple perspectives. Engaging the public through outreach and education will also inspire the next generation of scientists and ensure that the study of singularities remains a vibrant and inclusive field. As we look to the future, the study of singularities serves as a testament to the human spirit of inquiry. These enigmatic objects challenge us to confront the unknown, pushing the boundaries of knowledge and imagination. Whether through groundbreaking observations, theoretical insights, or technological innovations, the quest to understand singularities is a journey that will shape our understanding of the universe for generations to come. Cosmic simulations, modeling singularities. In the absence of direct access to singularities, scientists have turned to the next best approach: simulation. Cosmic simulations, powered by the most advanced supercomputers and algorithms, allow researchers to model the conditions near singularities and explore their behavior in ways that are impossible to replicate in physical laboratories. From the birth of black holes to the intricate dance of matter around event horizons, these virtual experiments are revolutionizing our understanding of singularities. But how do they work, and what are they revealing? Cosmic simulations begin with the mathematics of general relativity. Einstein's equations, which describe how mass and energy warp spacetime, serve as the foundation for modeling singularities. These equations are notoriously complex, involving nonlinear interactions that are difficult to solve analytically. However, with the power of modern computing, researchers can solve them numerically, creating detailed models of black holes, neutron stars, and the extreme environments where singularities reside. One of the most significant challenges in simulating singularities is their infinite density and curvature. Traditional computational methods struggle with these infinities, as they cause the equations to break down. To overcome this, scientists use techniques like regularization, which approximates the singularity with finite but extreme values, or employ alternative theories of gravity that avoid infinities altogether. These methods allow simulations to capture the behavior of matter and space-time near the singularity without becoming mathematically intractable. Simulations have proven invaluable in studying the formation and evolution of black holes. By modeling the collapse of massive stars, researchers can trace the conditions under which singularities form and predict their properties, such as mass, spin, and charge. These models also explore the dynamics of accretion disks, rings of gas and dust that spiral into black holes. and the powerful jets they produce. These phenomena are not only visually striking, but also key to understanding the role of singularities in shaping galaxies and the cosmos. Gravitational wave research has been particularly enriched by simulations. When black holes or neutron stars merge, they generate gravitational waves that ripple through space-time. Simulating these mergers allows scientists to predict the waveforms of these signals, which can then be compared with observations from detectors like LIGO and Virgo. These comparisons help confirm the existence of singularities and provide insights into their characteristics. One of the most ambitious goals of cosmic simulations is to explore the interiors of black holes and the behavior of singularities themselves. While the event horizon prevents direct observation of these regions, simulations can extrapolate the dynamics of matter and space-time beyond this boundary. These models probe questions such as, what happens to matter as it approaches a singularity? How do quantum effects influence the region near the Planck scale, where gravity and quantum mechanics intersect? Although these simulations remain speculative, they push the boundaries of our theoretical understanding. The study of naked singularities has also benefited from simulations. These hypothetical objects, lacking an event horizon, present unique challenges and opportunities for modeling. By simulating scenarios that might lead to the formation of naked singularities, such as the collapse of non-spherical stars or highly energetic collisions, researchers can test the cosmic censorship conjecture and explore the consequences of exposed singularities. Cosmic simulations extend beyond black holes to encompass the singularities associated with the Big Bang. Models of the early universe, such as those based on inflationary cosmology, simulate the conditions moments after the Big Bang, offering clues about its potential singularity. These simulations explore how quantum fluctuations seeded the large-scale structure of the universe and examine the transition from the quantum realm to the classical cosmos we observe today. The future of singularity simulations is tied to advancements in computing power and algorithms. Exascale computing, which performs quintillions of calculations per second, promises to revolutionize the field, enabling simulations of unprecedented complexity and resolution. Machine learning and artificial intelligence are also playing an increasingly important role, helping to optimize simulations and identify patterns in massive datasets. Simulations are not merely tools for confirming existing theories. They are also engines of discovery. By allowing researchers to test hypotheses and explore hypothetical scenarios, simulations often reveal unexpected phenomena and generate new questions. For example, simulations of binary black hole mergers have uncovered complex dynamics in gravitational wave signals, hinting at subtle effects that challenge our understanding of general relativity. As cosmic simulations grow more sophisticated, they are also becoming more accessible. Public platforms like Open Science Grid and distributed computing projects such as Einstein at Home enable citizen scientists to contribute to the computational effort. This democratization of simulation fosters collaboration and broadens the impact of singularity research. Cosmic simulations are more than just computational experiments. They are windows into realms we cannot physically reach. By modeling the behavior of singularities and the extreme environments around them, these simulations deepen our understanding of the universe's most enigmatic regions. As technology advances, they will continue to illuminate the mysteries of singularities, guiding us toward answers to questions that have long eluded humanity. The ethics of exploring singularities. As humanity delves deeper into the mysteries of singularities, questions of ethics and responsibility inevitably arise. These enigmatic phenomena, ranging from the cores of black holes to the theoretical Big Bang singularity, challenge not only the boundaries of science, but also our philosophical and moral frameworks. Should we attempt to manipulate singularities, harness their energy, or even create artificial black holes in laboratories? What are the risks of exploring such extremes, and what principles should guide our journey into the unknown? One of the most compelling ethical considerations is the potential danger posed by experimenting with singularities or black hole-like conditions. Advances in particle physics, particularly at high-energy colliders like the Large Hadron Collider (LHC), have sparked debates about the creation of microscopic black holes. While current theories suggest that such black holes would evaporate almost instantly via Hawking radiation, the possibility of unforeseen consequences cannot be dismissed. Could such experiments inadvertently trigger catastrophic events, such as a runaway singularity that consumes its surroundings? To address these concerns, scientists and policymakers must weigh the benefits of singularity research against its risks. This balance is not unique to black hole studies. It parallels debates in other high-stakes scientific fields, such as genetic engineering, artificial intelligence, and nuclear physics. Developing rigorous safety protocols, conducting thorough risk assessments, and fostering transparent communication between researchers and the public are essential steps in ensuring that the pursuit of knowledge does not endanger humanity. The ethical implications of exploring singularities extend beyond physical risks to questions of environmental and cosmic responsibility. Singularities, particularly those in black holes, represent some of the most extreme concentrations of energy in the universe. If we could harness this energy, it might offer solutions to global energy crises, providing an almost limitless power source. However, attempting to extract energy from black holes through methods such as the Penrose process or Hawking radiation raises concerns about the unintended consequences of interfering with these natural phenomena. Could such actions disrupt the delicate balance of a galaxy or even the broader cosmos? Another ethical dimension involves the potential exploitation of singularity research for military purposes. The extreme forces and energies associated with singularities could, in theory, be weaponized, leading to destructive capabilities far beyond current technologies. The prospect of black hole bombs or other singularity-based weapons necessitates proactive measures to prevent misuse. International agreements, akin to nuclear non-proliferation treaties, may be required to ensure that singularity research is conducted for peaceful purposes. The exploration of singularities also intersects with philosophical questions about the nature of existence and our place in the universe. Singularities, as regions where physical laws break down, confront us with the limits of human understanding. They challenge us to consider whether there are aspects of reality that are fundamentally unknowable or whether our pursuit of knowledge can overcome any boundary. This raises ethical questions about the scope of human ambition. Should we strive to unlock every mystery, or are there some realms best left unexplored? Cultural and societal perspectives further enrich the ethical discussion. Singularities often evoke awe and fear, blending scientific curiosity with existential reflection. Different cultures and belief systems may interpret these phenomena through diverse lenses, shaping attitudes toward their exploration. Respecting these perspectives and engaging in inclusive dialogues about the implications of singularity research can foster global collaboration and shared ethical standards. As we push the boundaries of singularity research, education and public engagement will play a crucial role in shaping its ethical trajectory. By demystifying singularities and explaining their significance in accessible terms, scientists can build trust and inspire public interest. Informed citizens are better equipped to participate in ethical debates and to advocate for responsible approaches to singularity exploration. Ultimately, the ethics of exploring singularities are inseparable from the broader question of how humanity should approach the unknown. Singularities represent the ultimate frontiers, where the familiar laws of physics give way to new possibilities and profound mysteries. Navigating these frontiers requires not only scientific rigor, but also humility, foresight, and a commitment to the common good. As we stand on the threshold of discoveries that could redefine our understanding of the universe, the choices we make today will shape the future of singularity research and its impact on humanity. By approaching these enigmatic phenomena with care and responsibility, we can ensure that the pursuit of knowledge remains a force for progress, inspiration, and wonder. The singularity and the end of the universe. As we peer into the cosmos, singularities, those enigmatic points where matter is infinitely dense and space-time infinitely curved, pose profound questions about the fate of the universe itself. Could singularities be harbingers of cosmic doom, or do they hold clues about the universe's ultimate destiny? Whether through the collapse of massive stars into black holes, the potential reversal of the Big Bang, or the evaporation of black holes via Hawking radiation, singularities are deeply intertwined with the life cycle of the cosmos. The concept of singularities as the endpoints of space-time first arises in the context of black holes. These objects, formed from the gravitational collapse of massive stars, serve as cosmic traps where nothing, not even light, can escape. Over time, black holes grow by accreting matter and merging with one another, potentially becoming supermassive black holes at the centers of galaxies. As stars die and galaxies evolve, black holes may increasingly dominate the universe, consuming nearby matter and energy. Could this lead to a future where singularities are the last remnants of cosmic structure? One possible scenario for the universe's fate involves the continued expansion driven by dark energy. Observations suggest that the universe is expanding at an accelerating rate, pulling galaxies apart and diluting matter and energy. In this heat-death scenario, the universe reaches a state of maximum entropy, where all energy is evenly distributed and no useful work can be done. Black holes, being some of the last structures to survive, would slowly evaporate through Hawking radiation over unfathomably long timescales, eventually leaving a cold, dark, and lifeless cosmos. Hawking radiation itself plays a crucial role in this narrative. As black holes emit radiation and lose mass, they gradually shrink and increase in temperature, emitting more radiation as they approach their final moments. The last stages of a black hole's life would culminate in a dramatic burst of radiation, dispersing its remaining energy into the surrounding space. This process marks the ultimate dissolution of singularities in the heat-death scenario, signaling the end of one of the universe's most enigmatic phenomena. An alternative vision of the universe's end involves the Big Rip, a dramatic and catastrophic scenario driven by dark energy. If the strength of dark energy increases over time, it could overcome all forces binding matter together, tearing apart galaxies, stars, planets, and even atomic nuclei. In this scenario, singularities might form as matter collapses under its own gravity in the moments before the universe is ripped apart entirely. These singularities would exist only briefly before the fabric of space-time itself disintegrates. Another possibility is the Big Crunch, a cyclical model in which the expansion of the universe eventually reverses, leading to a contraction phase. In this scenario, galaxies, stars, and eventually all matter collapse into a final singularity, a state of infinite density and temperature. This cosmic implosion could represent the end of our universe or the beginning of a new one, in a cyclic Big Bounce model where each collapse is followed by a new expansion. The cyclic model finds support in certain interpretations of quantum gravity, particularly those involving loop quantum cosmology. In this framework, space-time is quantized, and singularities are replaced with finite, highly dense regions. Instead of a singular Big Bang or Big Crunch, the universe transitions smoothly from one phase to another, avoiding the infinities predicted by classical physics. This elegant model suggests that singularities are not true endpoints, but rather gateways to new epochs of cosmic evolution. Singularities also intersect with multiverse theories, which propose that our universe is one of many. In this context, singularities might serve as connections between different universes, with black holes acting as portals to new realms. Alternatively, the singularity at the Big Bang might represent a point of origin for our universe within a broader multiverse landscape, where different regions of space-time follow distinct physical laws and histories. The study of primordial black holes, hypothetical remnants of the early universe, offers additional insights into the connection between singularities and cosmic evolution. If these objects exist, they could provide evidence for high-energy processes that occurred shortly after the Big Bang, shedding light on the initial conditions of our universe. Their detection would also illuminate the role of singularities in shaping the cosmos from its inception. Philosophically, the connection between singularities and the end of the universe raises profound questions about existence and time. If the universe ends in a singularity, does this mark a final conclusion, or is it merely a transition to another state? What happens to the information encoded in the universe's structure and history? These questions challenge our understanding of permanence and impermanence, forcing us to confront the ultimate limits of knowledge. The narrative of singularities and the universe's fate is not just a story of endings. It is also a story of beginnings. Singularities represent extremes where the known laws of physics break down, creating opportunities for new insights and discoveries. Whether as endpoints, transitions, or gateways, singularities invite us to reimagine the cosmos and our place within it. As we continue to explore singularities and their role in cosmic evolution, we are reminded of the interconnectedness of all things. From the birth of stars to the death of galaxies, from the Big Bang to the far future, singularities shape the universe's story, guiding us toward a deeper understanding of existence itself. Human fascination with singularities. Singularities are more than just astrophysical phenomena. They are symbols of mystery, extremes, and the boundaries of human understanding. From ancient myths about cosmic creation to cutting-edge scientific theories, the concept of singularities captivates the human imagination. What is it about these enigmatic objects that draws us in, and how have they shaped our quest for knowledge and meaning? At their core, singularities represent the ultimate unknown. They are regions where the familiar rules of physics and space-time cease to apply, forcing us to confront the limits of our comprehension. This aspect of singularities resonates deeply with the human spirit of exploration. Throughout history, humanity has been driven to uncover what lies beyond the horizon. Whether it be the edge of the known world, the depths of the ocean, or the vastness of space, singularities, as cosmic frontiers, embody this drive to explore the uncharted. The fascination with singularities is also rooted in their role as gateways to the infinite. Singularities are places where finite quantities, mass, density, curvature, reach boundless extremes. This interplay between the finite and the infinite echoes themes found in philosophy, religion, and art. Many cultures have grappled with the concept of infinity, associating it with the divine, the sublime, or the eternal. Singularities, as physical manifestations of infinity, provide a tangible connection to these abstract ideas. In modern times, singularities have become central to some of the most profound questions in science. The singularity at the heart of a black hole challenges our understanding of gravity, matter, and energy. The singularity associated with the Big Bang forces us to consider the origins of the universe and the nature of time itself. These questions go beyond physics, touching on existential themes about the nature of reality and humanity's place in the cosmos. Singularities also serve as a bridge between science and storytelling. They appear frequently in fiction, where their mysterious and extreme properties make them ideal plot devices. Black holes, for example, have been portrayed as portals to other dimensions, engines of destruction, and symbols of ultimate power. From films like Interstellar to novels like Arthur C. Clarke's 2001, A Space Odyssey, singularities inspire narratives that blend scientific speculation with human drama. In addition to their narrative appeal, singularities challenge us to rethink our relationship with the universe. The discovery of black holes and their singularities has transformed our understanding of cosmic structure, revealing a universe that is far more dynamic and interconnected than previously imagined. These discoveries invite us to see ourselves as part of a larger, more intricate whole, where the forces that shape singularities also influence the stars, planets, and life itself. The allure of singularities is not limited to their scientific and philosophical implications. They also evoke a sense of wonder and awe. The idea of a region where time slows, space twists, and matter is compressed to unimaginable densities captures the imagination in a way few other phenomena can. This sense of wonder has the power to inspire future generations of scientists, artists, and thinkers, encouraging them to pursue the mysteries of the cosmos. As we continue to study singularities, their symbolic significance grows alongside our scientific understanding. They remind us of the beauty and complexity of the universe, as well as the challenges and opportunities of exploring the unknown. Whether as scientific puzzles, philosophical conundrums, or sources of inspiration, singularities remain at the heart of humanity's quest to understand the cosmos and our place within it. The role of singularities in advancing human knowledge. Singularities stand as some of the most enigmatic features of the universe, yet their study has propelled advances across multiple domains of human knowledge. From theoretical physics to cosmology, philosophy, and even technology, Singularities challenge us to push the boundaries of understanding and develop new tools and theories. By confronting the mysteries of singularities, humanity not only unravels the secrets of the cosmos, but also drives progress in unexpected and transformative ways. Singularities and the evolution of physics. The exploration of singularities has been a driving force in the development of modern physics. The prediction of black hole singularities emerged from Einstein's general theory of relativity, marking one of the first intersections between theoretical predictions and the mysteries of extreme gravitational environments. However, the infinities associated with singularities revealed the limitations of general relativity, highlighting the need for a unified theory that could reconcile gravity with quantum mechanics. This pursuit of a quantum theory of gravity has led to groundbreaking work in fields like string theory, loop quantum gravity, and holography. String theory, for instance, reimagines particles as one-dimensional strings vibrating in multiple dimensions, potentially resolving the singularities of general relativity. Meanwhile, loop quantum gravity proposes that space-time itself is quantized, avoiding the infinite densities predicted by classical theories. These advances not only deepen our understanding of singularities, but also lay the groundwork for unifying the fundamental forces of nature. The influence of singularities on cosmology. Singularities are central to our understanding of the universe's origins and fate. The Big Bang, often described as a singularity, marks the beginning of space, time, and matter. Studying this primordial singularity has revolutionized cosmology, leading to the development of models such as cosmic inflation and the multiverse hypothesis. These theories provide insights into the early universe, the large-scale structure of the cosmos, and the potential existence of other universes. The study of black holes, which harbor singularities at their cores, has also reshaped our view of cosmic evolution. Black holes influence galaxy formation, regulate star formation, and act as engines for high-energy phenomena like quasars and gamma-ray bursts. Understanding these processes has profound implications for astrophysics and cosmology, revealing how singularities play a critical role in shaping the universe. Technological innovations driven by singularities. The study of singularities has spurred technological advancements that extend beyond astrophysics. The detection of gravitational waves, for example, required the development of highly sensitive instruments like LIGO and Virgo. These observatories rely on precision engineering, advanced lasers, and computational techniques that have applications in fields ranging from materials science to medical imaging. Similarly, the quest to understand singularities has driven the development of supercomputing and artificial intelligence. Simulating the extreme conditions near singularities requires immense computational power, leading to innovations in algorithms, hardware, and data processing. These technologies are now used in diverse areas, including climate modeling, drug discovery, and finance. Philosophical insights from singularities. Singularities challenge our understanding of reality, forcing us to grapple with questions about the nature of time, space, and existence. The breakdown of physical laws at singularities suggests that our current models of the universe are incomplete, prompting philosophical debates about the limits of human knowledge. Are singularities inherently unknowable, or are they simply beyond the reach of our current theories and tools? The study of singularities also raises ethical and existential questions. If singularities are connected to the origins and fate of the universe, what does this imply about humanity's role in the cosmic narrative? These questions resonate deeply with the human condition, inspiring reflection on our place in the universe and the meaning of our existence. Singularities as catalysts for collaboration. The study of singularities brings together diverse fields and disciplines, fostering collaboration between physicists, mathematicians, philosophers, and engineers. This interdisciplinary approach has not only advanced our understanding of singularities, but also created a model for addressing other complex scientific challenges. By pooling expertise and resources, researchers can tackle questions that transcend the boundaries of individual disciplines. The inspirational power of singularities. Beyond their scientific and philosophical significance, singularities inspire awe and wonder. They represent the ultimate frontier, where the known laws of physics give way to the unknown. This sense of mystery has captivated generations of scientists, artists, and dreamers, driving humanity to explore the cosmos and expand the limits of imagination. Singularities also play a central role in education and public engagement. By demystifying these phenomena and sharing their stories, scientists can inspire curiosity and foster a deeper appreciation for the universe. This engagement is crucial for cultivating the next generation of researchers and ensuring that the study of singularities remains a vibrant and inclusive field, a catalyst for the future. As we continue to study singularities, their influence on human knowledge will only grow. Advances in observational technology, theoretical frameworks, and computational methods will provide new insights into these enigmatic phenomena, transforming our understanding of the universe. At the same time, the questions posed by singularities will continue to challenge us, pushing the boundaries of science, philosophy, and technology. Singularities are more than just points in space-time. They are catalysts for progress and symbols of humanity's unending quest to understand the cosmos. By exploring these ultimate mysteries, we not only unlock the secrets of the universe, but also discover the limitless potential of human ingenuity and imagination. Cosmic connections. How singularities shape the universe. Singularities are not isolated phenomena, confined to the centers of black holes or the origins of the Big Bang. Instead, they are deeply interconnected with the cosmos, influencing everything from the formation of galaxies to the behavior of space-time itself. These connections reveal the profound ways singularities shape the universe, acting as both architects and catalysts in the cosmic drama. Singularities and galactic evolution. At the heart of nearly every galaxy lies a supermassive black hole, millions to billions of times the mass of the Sun. These colossal singularities are far more than passive observers. They actively shape the structure and dynamics of their host galaxies. Through processes like accretion and feedback, supermassive black holes regulate star formation, influence the distribution of gas and dust, and even determine the shape of galaxies. Accretion disks, composed of gas and matter spiraling into the black hole, emit enormous amounts of energy as they heat up. This energy can drive powerful jets of particles, extending thousands of light years into space. These jets, combined with the black hole's gravitational pull, redistribute material throughout the galaxy, creating an intricate balance between growth and suppression. Without these singularities, galaxies as we know them might not exist. Singularities as star factories. While singularities are often associated with destruction, they also play a role in creation. The intense gravitational pull of black holes can compress gas clouds, triggering the formation of new stars. This process, known as starburst activity, is particularly common in galaxies undergoing mergers, where interactions between singularities and interstellar matter create regions of rapid star formation. Similarly, the remnants of stars that collapse into singularities, stellar mass black holes, and neutron stars, serve as markers of stellar evolution. By studying these remnants, scientists gain insights into the life cycles of stars and the processes that govern their birth, death, and rebirth. Singularities and the large-scale structure of the universe. Singularities are intimately connected to the large-scale structure of the universe. During the early moments after the Big Bang, quantum fluctuations in the primordial singularity created tiny density variations in the fabric of space-time. Over billions of years, these variations grew into the vast cosmic web of galaxies, clusters, and voids that we observe today. The gravitational influence of black holes, which are themselves singularities, further shape this structure. By anchoring galaxies and clustering matter, singularities acted as seeds for the formation of complex cosmic patterns. Without these initial conditions, the universe might have remained a homogeneous expanse of gas and radiation. Singularities in time. The influence of singularities extends beyond matter and energy to the very nature of time. Singularities, as regions where space-time curvature becomes infinite, challenge our understanding of temporal flow. Near a singularity, time slows dramatically due to intense gravitational time dilation, a phenomenon confirmed by general relativity. These effects are not confined to the immediate vicinity of singularities. They influence the broader behavior of space-time, creating a dynamic interplay between the expansion of the universe and the gravitational pull of massive objects. Singularities, as focal points of extreme gravity, act as anchors in the ever-evolving fabric of the cosmos. Singularities and the search for dark matter and dark energy. The study of singularities intersects with two of the greatest mysteries in modern cosmology: dark matter and dark energy. Black holes, which harbor singularities, provide indirect evidence for dark matter through their interactions with visible matter. Observing the motion of stars and gas near black holes reveals the presence of unseen mass, offering clues about the nature of dark matter. Dark energy, the force driving the accelerated expansion of the universe, may also have connections to singularities. Some theories propose that singularities influence the vacuum energy of spacetime, contributing to the effects attributed to dark energy. While these ideas remain speculative, they highlight the potential role of singularities in unraveling the mysteries of the cosmos. Singularities and the multiverse. Singularities are also central to theories of the multiverse. If our universe originated from a singularity at the Big Bang, could other universes have emerged from similar conditions? Some models suggest that singularities might serve as gateways between universes, connecting disparate regions of a vast multiverse. Black holes, in particular, are thought to create conditions that could spawn new universes, with their singularities acting as cosmic birth canals. The unified influence of singularities. From the smallest scales of quantum fluctuations to the largest structures of galaxies and cosmic filaments, singularities play a unifying role in the universe. They bridge the gap between the microscopic and macroscopic, linking the behavior of particles to the dynamics of entire galaxies. Their influence extends across time and space, shaping the past, present, and future of the cosmos. Singularities and human understanding. As we study these cosmic connections, singularities deepen our understanding of the universe and our place within it. They remind us of the interconnectedness of all things, revealing a universe where every structure, from the tiniest particle to the largest galaxy, is part of a greater whole. Singularities challenge us to confront the unknown, pushing the boundaries of science and imagination. In exploring the role of singularities in shaping the universe, we come to appreciate their dual nature: destructive yet creative, enigmatic yet illuminating. Singularities are not just endpoints. They are the nexus of cosmic forces, driving the evolution and complexity of the universe. Through them, we glimpse the profound beauty and interconnectedness of existence, human curiosity, and the limitless pursuit of singularities. The study of singularities is not merely a quest for scientific understanding. It is a reflection of humanity's intrinsic curiosity and our relentless drive to explore the unknown. Singularities, with their paradoxical nature and cosmic significance, encapsulate the spirit of discovery that has propelled human progress for millennia. But what does our fascination with singularities reveal about us? And how does this pursuit shape our future? Singularities as a reflection of human curiosity. Throughout history, humanity has sought to unravel the mysteries of existence, asking questions about the origins of the universe, the nature of time, and the boundaries of reality. Singularities sit at the nexus of these inquiries, embodying the ultimate unknown. Their study requires us to confront the edges of our understanding, pushing the limits of physics, mathematics, and philosophy. The allure of singularities lies in their dual nature. They are both deeply theoretical and profoundly real, existing as solutions to Einstein's equations and as physical entities in the form of black holes and the Big Bang. This combination of abstraction and tangibility makes singularities uniquely compelling, bridging the gap between the conceptual and the observable. Singularities and the spirit of exploration. Singularities represent a frontier, a place where the familiar rules of physics break down and new possibilities emerge. This sense of a boundary to be crossed resonates deeply with the human spirit of exploration. Just as ancient navigators ventured beyond the known world and astronauts journeyed into space, scientists probe the mysteries of singularities, driven by the same desire to chart the uncharted. The exploration of singularities is not limited to academic research. It is also a cultural and imaginative endeavor. Stories about black holes, wormholes, and the Big Bang inspire wonder and spark curiosity, encouraging people of all ages and backgrounds to engage with the cosmos. This universal appeal underscores the power of singularities to connect us to the larger narrative of human discovery. Singularities and the evolution of thought. Studying singularities challenges us to think in new ways, often requiring radical shifts in perspective. The development of general relativity, for example, revolutionized our understanding of gravity, space-time, and the universe itself. Similarly, the pursuit of a quantum theory of gravity is reshaping our understanding of the fundamental forces that govern reality. These intellectual breakthroughs have broader implications, influencing not only science but also philosophy, art, and culture. Singularities inspire questions about the nature of existence, the limits of knowledge, and humanity's place in the cosmos. By exploring these questions, we expand the scope of human thought and deepen our appreciation for the complexity of the universe. The role of technology in unlocking singularities. The study of singularities is intimately tied to technological innovation. Instruments like the Event Horizon Telescope, LIGO, and advanced particle accelerators provide the tools necessary to probe the extreme environments where singularities reside. These technologies, in turn, drive advancements in fields ranging from computing to engineering, creating a virtuous cycle of discovery and innovation. Future technologies, such as quantum computers and space-based observatories, promise to unlock even more insights into singularities. These tools will enable simulations of black holes, detailed studies of gravitational waves, and investigations into the quantum properties of space-time. As technology evolves, so too will our ability to understand and explore singularities. The ethical dimensions of singularities. The pursuit of singularities also raises important ethical questions. Should we attempt to manipulate or create singularities, given the potential risks? How should we balance the quest for knowledge with the need to protect our planet and its inhabitants? These questions highlight the responsibility that comes with exploring such powerful and mysterious phenomena. By fostering dialogue about the ethical implications of singularity research, we can ensure that this pursuit is guided by principles of safety, sustainability, and equity. This approach not only safeguards humanity, but also honors the deeper values that drive our exploration of the universe. Singularities and the future of humanity. As we continue to study singularities, they will play an increasingly central role in shaping our understanding of the cosmos and our place within it. They offer a window into the most extreme conditions imaginable, providing insights that could transform our knowledge of physics, cosmology, and the origins of the universe. Beyond their scientific significance, singularities inspire us to dream. They remind us of the boundless possibilities of discovery and the limitless potential of human ingenuity. In exploring singularities, we are not just seeking answers to cosmic questions. We are affirming the spirit of curiosity and creativity that defines us as a species. Singularities are more than scientific puzzles. They are a testament to humanity's enduring quest to understand the universe. As we continue this journey, we are reminded that the greatest discoveries often lie at the edges of our knowledge, waiting to be revealed by those bold enough to venture into the unknown. Singularities and the quest for a unified theory. The study of singularities has illuminated profound gaps in our understanding of the universe. At the heart of these mysteries lies the need for a unified theory, a framework that seamlessly integrates the forces of nature and resolves the tensions between general relativity and quantum mechanics. Singularities, where these two pillars of modern physics collide, provide the ultimate testing ground for this long-sought goal. What progress has been made in this quest, and how might singularities guide us toward the answers? The conflict between relativity and quantum mechanics. General relativity, formulated by Albert Einstein, excels at describing the large-scale structure of the universe. It explains how gravity shapes space-time and governs the behavior of stars, planets, and galaxies. Quantum mechanics, by contrast, rules the microscopic realm, describing the behavior of particles, waves, and fields at atomic and subatomic scales. Singularities expose a fundamental incompatibility between these theories. General relativity predicts that singularities form in regions of extreme gravity, such as the centers of black holes, where space-time curvature becomes infinite. Quantum mechanics, however, does not permit infinities, suggesting that these descriptions are incomplete. Reconciling these two frameworks requires a theory of quantum gravity, a unified description of nature's fundamental forces. Singularities as laboratories for quantum gravity. Singularities represent the ultimate test of any candidate for quantum gravity. The extreme conditions near a singularity combine the immense gravitational pull predicted by relativity with the quantum scale behavior of particles. A successful theory must describe how space-time behaves at these scales, resolving the infinities predicted by classical physics while preserving the probabilistic nature of quantum mechanics. Theories like string theory and loop quantum gravity offer promising avenues for understanding singularities. String theory replaces point-like particles with tiny, vibrating strings, avoiding the infinities of general relativity. It also introduces extra dimensions, which could influence the behavior of singularities and potentially eliminate the need for a point-like singularity altogether. Loop quantum gravity, meanwhile, proposes that space-time itself is quantized, composed of discrete units that prevent infinite curvature. Black holes as windows into quantum gravity. Black holes, which harbor singularities at their cores, serve as natural laboratories for studying quantum gravity. The event horizon of a black hole, the boundary beyond which nothing can escape, provides a surface where quantum effects and relativistic predictions intersect. By studying phenomena like Hawking radiation, scientists can probe the interplay between gravity and quantum mechanics, gaining insights into the nature of singularities. The information paradox, which questions whether information falling into a black hole is truly lost, is a key challenge in this research. Resolving this paradox requires a better understanding of how quantum information is stored, transferred, or preserved in the context of singularities. Solutions to this puzzle could provide critical clues about the underlying principles of quantum gravity. The role of simulations and experiments. Advances in computational physics have enabled detailed simulations of black holes, mergers, and the environments near singularities. These simulations test the predictions of candidate quantum gravity theories, revealing where they align with or deviate from observational evidence. For example, gravitational wave data from events like black hole mergers provide real-world constraints on theoretical models, helping scientists refine their understanding of singularities. Laboratory experiments, while unable to replicate the conditions near singularities directly, have also contributed to this quest. Analog systems, such as fluid dynamic setups that mimic event horizons, allow researchers to study the behavior of waves, particles, and fields in controlled environments. These analog experiments provide valuable insights into how singularities might behave under extreme conditions. The philosophical implications of a unified theory. The search for a unified theory goes beyond physics, raising profound philosophical questions about the nature of reality. What does it mean for the universe to have a single set of underlying laws? If singularities are resolved within a unified framework, do they still represent the limits of our knowledge, or do they reveal new layers of complexity? These questions touch on the very essence of human curiosity, inspiring us to explore not only the mechanics of the universe, but also its meaning. Singularities, as places where the known laws of physics break down, challenge us to rethink our assumptions about the cosmos and our place within it, toward a unified understanding. While the quest for a unified theory is far from complete, the study of singularities continues to drive progress. Each discovery, whether theoretical or observational, brings us closer to a comprehensive understanding of nature's fundamental forces. Singularities act as both puzzles and guideposts, highlighting the gaps in our knowledge and pointing the way toward deeper truths. The pursuit of a unified theory is a testament to the power of human ingenuity and perseverance. It reflects our enduring desire to make sense of the universe, to connect the dots between the smallest particles and the largest cosmic structures. As we journey toward this goal, singularities remain at the center of our quest, challenging us to unravel their mysteries and unlock the secrets of existence itself. The interplay of singularities and consciousness. As the mysteries of singularities continue to challenge our understanding of the universe, a fascinating question emerges. Could the study of singularities have implications for our understanding of consciousness? This may seem like an unlikely connection at first glance, but both singularities and consciousness represent profound mysteries, enigmas where the known laws of nature appear to break down. Could these two domains, seemingly worlds apart, be linked in ways we have yet to grasp? Singularities as extremes of experience. Singularities are regions of space-time where gravity reaches unimaginable strengths and space-time curvature becomes infinite. They are characterized by phenomena that defy conventional understanding, such as time dilation and the breakdown of causality. Similarly, consciousness is a phenomenon that transcends simple explanations, involving subjective experiences, self-awareness, and the ability to reflect on the universe. The analogy between singularities and consciousness lies in their shared role as boundaries of knowledge. Singularities represent the edge of physical understanding, where the laws of physics falter. Consciousness, on the other hand, is often described as the hard problem of neuroscience and philosophy, a phenomenon that resists reduction to purely physical processes. Both invite us to consider the limits of human comprehension and the possibility of deeper, interconnected truths. Quantum mechanics, singularities, and the mind. Quantum mechanics plays a central role in the study of singularities, particularly in the quest for a theory of quantum gravity. Interestingly, quantum mechanics also intersects with theories of consciousness. Some researchers have proposed that quantum processes in the brain could underlie aspects of conscious experience, though this idea remains controversial. Singularities, as extreme environments where quantum effects dominate, may offer insights into the nature of reality that also inform our understanding of consciousness. For instance, the phenomenon of entanglement, a cornerstone of quantum mechanics, raises questions about the interconnectedness of seemingly separate entities. Could this principle, observed near singularities, have parallels in the way consciousness arises from the interactions of neurons or other systems? Singularities and the nature of reality. Both singularities and consciousness challenge our perceptions of reality. Singularities, by warping space-time and creating horizons of no return, alter the way we think about space, time, and causality. Similarly, consciousness shapes our subjective experience of reality, filtering and interpreting the external world in ways that remain deeply personal and enigmatic. The interplay between singularities and consciousness may be more than metaphorical. Some theories suggest that the universe itself could be conscious, with singularities playing a role in this cosmic awareness. While such ideas are speculative, they align with certain interpretations of panpsychism, the view that consciousness is a fundamental aspect of the universe, woven into its very fabric. The philosophical dimensions of singularities and consciousness. Philosophers have long grappled with the implications of singularities and consciousness for our understanding of existence. Singularities force us to confront the idea that the universe contains regions where our theories break down, inviting us to consider what lies beyond our current knowledge. Consciousness, by revealing the subjective nature of experience, challenges the notion of an entirely objective reality. The intersection of these domains invites profound questions. Could singularities represent gateways to new forms of understanding, not only of the physical universe but also of consciousness? Do they offer a glimpse into dimensions or realities that transcend our current frameworks? And could the study of singularities ultimately provide insights into the nature of the mind itself? Technological and theoretical advances. Advances in technology and theory may help bridge the gap between singularities and consciousness. High-resolution simulations of singularities and their environments could reveal patterns and structures that inform broader philosophical and scientific questions. Meanwhile, breakthroughs in neuroscience and artificial intelligence could provide analogies or models that shed light on the nature of singularities. For example, the development of neural networks and machine learning has already influenced the study of cosmology and black holes. These tools could be used to identify connections between complex systems, whether in the brain or in the dynamics of spacetime, revealing parallels that deepen our understanding of both. a shared frontier. The study of singularities and consciousness reflects humanity's quest to understand the ultimate questions. What is the nature of reality? How does the universe function at its most fundamental level? And what is our place within this vast and intricate cosmos? While singularities represent the extremes of the physical universe, and consciousness delves into the depths of subjective experience, both challenge us to think beyond conventional boundaries. Together, they inspire new ways of thinking, encouraging us to explore the connections between the outer cosmos and the inner mind. As we continue to investigate these profound mysteries, we may find that singularities and consciousness share more than a conceptual link. They may reveal fundamental truths about the universe and ourselves, offering insights that transcend the divisions between science, philosophy, and the human experience. Singularities and the legacy of discovery. The exploration of singularities is more than an intellectual pursuit. It is a legacy of human curiosity and a testament to our drive to uncover the unknown. From the early formulations of gravitational theory to the discovery of black holes and the birth of modern cosmology, singularities have served as milestones in our journey to understand the universe. As we look to the future, the study of singularities continues to inspire groundbreaking research, technological innovation, and a deeper connection to the cosmos. The historical milestones of singularity research. The story of singularities begins with the foundations of modern physics. Isaac Newton's theory of gravity provided the first framework for understanding how massive objects interact, but it was Albert Einstein's general theory of relativity that introduced the concept of spacetime curvature. Einstein's equations predicted regions of infinite density and curvature, singularities, but these ideas were initially dismissed as mathematical oddities. Theoretical breakthroughs in the mid-20th century, led by figures such as Robert Oppenheimer, Roger Penrose, and Stephen Hawking, established singularities as real and inevitable consequences of gravitational collapse. The discovery of black holes as astrophysical objects confirmed the existence of event horizons, providing indirect evidence for the singularities they harbor. These findings transformed singularities from abstract curiosities into central players in the cosmic narrative. The modern era, observations and innovations. The modern study of singularities has been revolutionized by technological advances. Instruments like the Event Horizon Telescope have provided direct images of black holes, offering unprecedented insights into the environments near singularities. Gravitational wave observatories have detected the ripples created by black hole mergers, allowing scientists to study these phenomena with remarkable precision. Simulations and computational models have also played a crucial role. By solving Einstein's equations numerically, researchers have visualized the formation, evolution, and interactions of singularities in ways that were previously unimaginable. These tools have enabled the testing of theoretical predictions and inspired new lines of inquiry. Singularities as catalysts for theoretical progress. Singularities continue to drive the quest for a unified theory of physics. By challenging the compatibility of general relativity and quantum mechanics, they have spurred the development of theories such as string theory, loop quantum gravity, and the holographic principle. These frameworks not only aim to resolve the paradoxes associated with singularities, but also offer broader insights into the nature of spacetime, matter, and energy. The information paradox, in particular, remains a focal point of singularity research. Resolving this puzzle requires a deeper understanding of how information is stored, transferred, and preserved in the context of black holes. The search for answers has implications that extend beyond singularities, potentially transforming our understanding of quantum mechanics and thermodynamics. Singularities and humanity's future. The study of singularities has profound implications for the future of humanity. These enigmatic phenomena challenge us to develop new technologies, expand our theoretical frameworks, and explore the cosmos in ways that were once considered science fiction. From space exploration to advancements in artificial intelligence and quantum computing, the tools we develop to study singularities will shape our capabilities in a wide range of fields. Singularities also inspire us to think beyond our immediate horizons. They remind us of the vastness and complexity of the universe, encouraging us to approach the unknown with curiosity, humility, and a sense of wonder. By exploring singularities, We not only deepen our understanding of the cosmos, but also affirm our place as participants in a broader, interconnected reality. Singularities as a symbol of human aspiration. Throughout history, singularities have symbolized the extremes of nature and the limits of knowledge. They represent the boundaries where our current understanding falters and new possibilities emerge. In this sense, singularities are more than just physical phenomena. They are symbols of human aspiration, the drive to push beyond what is known and explore the uncharted. As we continue to study singularities, their legacy will endure as a testament to the power of human curiosity and creativity. They challenge us to ask profound questions, seek bold answers, and imagine new futures. Singularities, as both mysteries and milestones, embody the essence of discovery. Singularities and the interconnected universe. As we near the culmination of our exploration into singularities, it becomes increasingly clear that these enigmatic phenomena are not isolated anomalies, but integral components of an interconnected universe. Singularities influence the formation of galaxies, drive the dynamics of space-time, and challenge the boundaries of physics and philosophy. They are deeply woven into the cosmic fabric, offering insights into the unity and complexity of the cosmos. Singularities and the unity of forces. One of the most profound aspects of singularities is their ability to unify the fundamental forces of nature. In the extreme conditions near a singularity, gravity, electromagnetism, and the strong and weak nuclear forces converge. This convergence challenges physicists to develop a theory of quantum gravity that can describe these interactions within a single framework. The pursuit of a unified theory is not merely a theoretical exercise. It has practical implications for understanding the universe's origins and ultimate fate. Singularities serve as natural laboratories for testing these theories, providing a unique window into the interconnectedness of the forces that shape reality. The cosmic web and singularities. Singularities are also deeply connected to the large-scale structure of the universe. The gravitational pull of black holes, which harbor singularities at their cores, influences the distribution of matter and energy across vast distances. This interaction shapes the cosmic web, a sprawling network of galaxies, clusters, and voids that forms the backbone of the universe. The interplay between singularities and the cosmic web highlights the interconnected nature of the universe. Singularities, despite their localized extremes, have far-reaching effects that ripple across space-time. This dynamic interaction underscores the idea that the universe is a unified whole, where seemingly isolated phenomena are part of a greater, interdependent system. Singularities and the flow of time. The influence of singularities extends beyond space to the dimension of time. Near a singularity, time behaves in ways that challenge our conventional understanding. Gravitational time dilation slows the flow of time near massive objects, creating a relative experience of temporality that connects singularities to broader questions about the nature of time. This connection has profound implications for cosmology and metaphysics. Singularities force us to consider whether time is a fundamental aspect of the universe or an emergent property of space-time dynamics. By studying singularities, we gain insights into the temporal fabric of the cosmos and its relationship to the spatial dimensions. Singularities as gateways. Theoretical models suggest that singularities may serve as gateways to other regions of space-time, dimensions, or even universes. Wormholes, for example, are hypothetical structures that could connect disparate points in space-time, with singularities playing a central role in their formation. Similarly, some interpretations of black hole dynamics propose that matter falling into a singularity might emerge in another universe, suggesting a deeper interconnectedness between realities. While these ideas remain speculative, they illustrate the potential of singularities to bridge seemingly separate domains. Singularities, as focal points of extreme gravitational and quantum effects, challenge the notion of isolation and encourage us to think about the universe as a deeply connected system. Singularities and human understanding. The study of singularities mirrors humanity's quest to understand the universe's interconnectedness. By exploring these phenomena, we confront questions about the nature of existence, the unity of physical laws, and the relationships between the microcosm and the macrocosm. Singularities serve as a lens through which we can view the intricate web of connections that defines the cosmos. This perspective has broader implications for science, philosophy, and culture. It encourages interdisciplinary collaboration, fosters a sense of wonder, and inspires new ways of thinking about the universe and our place within it. Singularities, as both physical and conceptual phenomena, challenge us to embrace the complexity and beauty of the interconnected universe. A unified vision of singularities. As we conclude this exploration, it is clear that singularities are not merely endpoints in space-time or curiosities in the equations of physics. They are central to the story of the universe, influencing its structure, dynamics, and evolution. Singularities remind us that the cosmos is a tapestry of interconnected phenomena, where every part contributes to the whole. Through the study of singularities, we gain not only scientific insights, but also a deeper appreciation for the unity and diversity of the universe. These enigmatic objects inspire us to explore, question, and discover, driving humanity's journey toward understanding the interconnected nature of reality. Singularities and the infinite horizon of knowledge. Singularities are more than just cosmic phenomena. They are symbols of the infinite horizons of human knowledge. These enigmatic points in space-time challenge us to think beyond established frameworks, pushing the boundaries of science, philosophy, and imagination. As we close this exploration, it is worth reflecting on how singularities shape our understanding of the universe and illuminate the path forward in our quest for knowledge. Singularities as catalysts for innovation. Throughout history, singularities have driven some of the most significant advancements in science and technology. The mathematical prediction of singularities in general relativity inspired the study of black holes, leading to breakthroughs in astrophysics and cosmology. Observational evidence, such as gravitational waves and the first image of a black hole, has been made possible by innovations in technology, computation, and collaboration. These advancements underscore the interconnectedness of scientific disciplines. Singularities challenge not only physicists but also engineers, mathematicians, and computer scientists to develop new tools and theories. This collaborative effort exemplifies the power of interdisciplinary research and its ability to address the most profound questions about the universe. Singularities and the expansion of human perspective. Singularities force us to confront the limits of our understanding, both scientifically and philosophically. They reveal regions of space-time where our current theories break down, pointing the way to new frameworks and paradigms. In doing so, they expand our perspective on the universe and our place within it. By studying singularities, we gain insights into the nature of space-time, the origins of the universe, and the fundamental forces that govern reality. These discoveries challenge us to rethink concepts like causality, time, and infinity, encouraging us to adopt a more nuanced and interconnected view of existence. Singularities and the ethical horizon. As we advance in our understanding of singularities, we must also consider the ethical implications of this knowledge. The potential to manipulate singularities or harness their energy raises questions about responsibility and stewardship. How can we ensure that our pursuit of knowledge benefits humanity and respects the cosmos? These questions highlight the importance of ethical considerations in scientific research. By fostering dialogue and reflection, we can navigate the challenges and opportunities presented by singularities, ensuring that their study contributes to the greater good. The legacy of singularities. Singularities are not just endpoints in the universe. They are milestones in humanity's journey of discovery. They represent the extremes of nature and the limits of our understanding, inspiring us to explore, innovate, and dream. As we continue to study singularities, their legacy will endure as a testament to the power of curiosity and the human spirit. The future of singularities. The study of singularities is far from complete. Advances in technology, theory, and observation will uncover new mysteries and deepen our understanding of these enigmatic phenomena. Whether through the development of quantum gravity, the exploration of black holes, or the search for connections between singularities and the broader cosmos, the future promises to be as transformative as the discoveries that have come before. Singularities invite us to embrace the infinite horizon of knowledge, pushing beyond the boundaries of what we know and daring to ask questions that have yet to be imagined. They remind us that the universe is vast, complex, and interconnected, offering endless opportunities for exploration and discovery. As we conclude this journey, singularities stand as both challenges and inspirations, driving humanity to seek the answers that lie beyond the event horizon of our understanding. The study of singularities is not just about solving equations or testing theories. It is about uncovering the deeper truths of the cosmos and our place within it. Singularities, a journey without end. As we conclude this exploration of singularities, it is fitting to reflect on their role, not just as objects of study, but as symbols of humanity's boundless curiosity and imagination. Singularities stand at the crossroads of science, philosophy, and wonder, inviting us to probe the limits of the universe and the boundaries of our understanding. They embody the paradoxical nature of discovery. The more we learn about them, the more questions they raise. The eternal mystery of singularities. Singularities are unique in their capacity to simultaneously represent both what we know and what we do not. They emerge naturally from the mathematics of general relativity, yet they also expose the incompleteness of our theories. They are physical phenomena that defy observation, theoretical constructs that demand resolution, and metaphysical puzzles that challenge our perception of reality. This duality ensures that singularities will remain a focal point of inquiry, driving progress in fields as diverse as astrophysics, cosmology, mathematics, and quantum mechanics. They remind us that the universe is not a static collection of facts, but a dynamic and evolving mystery, one that we are constantly unraveling. Singularities and the human spirit. The study of singularities mirrors the qualities that define the human spirit: curiosity, creativity, and resilience. These enigmatic objects challenge us to think in new ways, to question established paradigms, and to seek answers in the face of uncertainty. They inspire collaboration across disciplines and generations, fostering a collective pursuit of knowledge that transcends individual efforts. Singularities also evoke a sense of humility. They remind us that the universe is vast and complex, operating on scales of time, space, and energy that dwarf human experience. Yet, they also affirm our ability to comprehend and engage with this vastness, to ask profound questions and seek meaningful answers. The enduring legacy of singularities. As we advance in our understanding of singularities, their influence will extend far beyond the realm of science. They will continue to shape our philosophies, inform our technologies, and inspire our imaginations. Whether as gateways to new theories or as metaphors for the unknown, singularities will remain central to humanity's exploration of the cosmos. This journey is far from over. Each new discovery about singularities opens the door to further questions, ensuring that their study is an ever-evolving endeavor. Singularities are not endpoints but horizons, places where the limits of our knowledge meet the infinite possibilities of the universe. A call to wonder. In contemplating singularities, we are reminded of the beauty and complexity of the cosmos. These phenomena invite us to look beyond the confines of our world and embrace the wonder of existence itself. They challenge us to be explorers, thinkers, and dreamers, ever reaching toward the mysteries that lie beyond. As we gaze into the depths of the universe, singularities reflect back not just the mechanics of space-time, but the essence of what it means to be human, the desire to understand, to create, and to connect. They are both a mystery to be solved and a mirror in which we see ourselves. The journey continues. While this exploration of singularities comes to a close, the journey they inspire continues. With each question we answer, new ones arise, ensuring that the study of singularities will remain a source of fascination and discovery for generations to come. Thank you for embarking on this cosmic journey. If there is anything more you wish to explore or discuss, let me know. The universe is vast, and the possibilities are endless.